Good morning. We are going to start in a few minutes. Please take your seats. Thank you for your participation in the symposium in honor of Professor Ilya Yablonovich. This is the Franklin Institute's award in electrical engineering, and Professor Ilya Yablonovich is a highly distinguished faculty member, innovator, scientist, and also a great personality. In a very short time that I had met him, he had made an indelible impression on me in his gentleness and kindness in many regards. And I'm sure some of his old friends, former students that are here, they all vouched for it, as you're going to hear from Professor Dan Siebenpiper, who wanted to be here, but unfortunately, being in academics, not everyone is able to make it. And I greatly appreciate some of our distinguished speakers that they shuffled their program to be able to make it. The event today is primarily a very long legacy of the Franklin Institute. In fact, this legacy goes back to 1824, the oldest science and technology award. Very few awards that are given to engineers, but this is one of the most prominent one in many respects. And in fact, if you look at the booklets that you all have received, you will see a little bit of history of the Benjamin Franklin Medal. And in particular, I have highlighted the fact that Professor Ilya Yablonovich, director of the NSF Center for Engineering Efficient Electronic Science, E3S, and we are going to hear novel, great ideas that are not only related to the photonic band gap and electromagnetic band gap, but also how you can apply it for a variety of applications. And one important application that we are going to hear about from our last two speakers is dealing with the solar energy and the impact of it. And Professor Yablonovich has contributed to the conceptualization and experimental demonstration, and that's the important distinction that we make, experimental demonstration, the first one ever, on photonic and electromagnetic bandgap engineering, and then its use in the confinement of electromagnetic waves. Extremely important, and I'm sure many of us that are very much enjoying Maxwell's equation recognize that how important electromagnetics is in all regards. And it has many applications, such as the photonic microwave and antenna structures, and we are going to hear from a number of speakers that are going to address these salient points. As I had indicated, the Franklin Institute Awards dates back to 1824, and it is considered one of the most prestigious awards in science and engineering. This honor has been bestowed to likes of Guillermo Marconi, Nikola Tesla, Thomas Edison, Lord Rayleigh, Max Planck, William Bragg, Albert Einstein, and also Sir Raman, Sergei Shelkonov, Jack Kilby, and Robert Noyce, and also late Professor Zorev, Alferev, who recently passed away, and Federico Capasso, and also Professor Daniel Tsui. I had selected these names in collaboration with my co-sponsor, Professor Ahmad Hurfar, because of the relevancy of these awardees to the theme of this symposium. Drexel University has recently celebrated Professor Manija Razegi. She wanted to be here, but as you know, most of faculty members, they have to do research activity, and the sponsors are very demanding. And she had a meeting with her Army Research Office, and she wanted to be here and personally congratulate you in the morning, but she ended up coming in the afternoon. And also Professor Nick Holniak, 2017 Franklin medalist, Professor Kenichi Iga, the Bauer Award of 2013, and Drexel's alumni, and also a great contributor to what we rely on in terms of the packet switching and internet, Paul Barron, who received the Bauer Award in 2001. It is a pleasure for me as a instrument in here today as part of the Drexel University community to celebrate the contribution of the Professor Jablonovich. And it is a great honor for Drexel University to host a symposium in his honor for his accomplishments. And the theme of this symposium, as I mentioned, and as you see, is a novel photonic and electromagnetic bandgap engineering. And without any further ado, I just want to give the floor to Professor Alistair Saunders, who is the Senior Vice Provost for Research at Drexel University.
Thank you.
Thank you.
Good morning, everyone. Welcome to my colleagues, to our visitors, and our honored guests. Congratulations, Dr. Jablonovich. Spring is one of my favorite times of the year, not just because we have light till 7 p.m. and the flowers are blooming, but that in this time of year in Philadelphia, we get to celebrate the birth of novel ideas and innovations, and most importantly, the innovators that brought those ideas to us. This week is a plethora of brilliant minds, innovators, world thought leaders, and we're so excited to be able to host part of the Franklin Medal Award ceremony. So today, it is our honor to host this celebration, which looks back and I think forward, celebrating the impressive innovations of Dr. Jablonovich. So I want to thank Afshin and your colleague from Villanova for putting this together, everyone that's visiting from afar, my colleagues, and congratulations, Dr. Jablonovich. Have a wonderful time. I'll see you tomorrow night. It's so impressive. It's such a celebration of ideas and the people that bring those ideas to society. So congratulations. Cheers.
Hardy laser pointers, they survive. I'd like to also invite Professor Jerry Jones, who wears two hats today, not only as a professor of mechanical engineering. You are among minority here.
We're all engineers.
Yes, exactly. And also the past chair of the Committee on Sciences and the Arts of the Franklin Institute. Jerry, I would appreciate if you welcome. Yes.
Good morning, and welcome to all of you, and thank you for allowing me to come out here this morning and give this brief welcome to our astute audience at this symposium, and especially Professor Jablonovich, who we look forward to hearing more tonight at a dinner at the Franklin Institute, and also tomorrow night at the award ceremony, which we all look forward to very much. So I just want to say that the College of Engineering in Villanova are very happy to have helped sponsor this symposium that celebrates the seminal contributions of Professor Jablonovich, Director of the National Science Foundation Center for Energy Efficient Electronics Science at UC Berkeley. By the way, I mentioned to Professor Jablonovich right before the talk that Villanova has an NSF-funded IUCRC center called ES2, Energy Smart Electronic Systems, which is very similar in name and almost acronym to his own center. Ours is directed at looking at making data centers more energy efficient. Of course, energy centers consume about 3% of the consumption of energy worldwide. So this week we celebrate the wonder and profound influence that science and engineering have on society. The week becomes even more impactful because of the stimulating dialogue and educational opportunities for both the technical and lay communities from the symposia for the 6 Franklin medal laureates, one of which we're attending today. My symposium is going on right now at Temple University for our laureate in mechanical and civil engineering. As it was pointed out before, I guess we're all going to scoop one another on this, and I'm probably scooping Darrell on this as well. The Institute's awards program dates to 1824, where a lot of the awards given back in that era were for the mechanical arts, because it's the Committee on Science and the Arts, the CS&A, that decides these award winners. And the A is not arts in terms of fine arts, it's mechanical arts. It's farming equipment, right? We'll see a lot of awards for that kind of thing if you go back through the archives in that era. It's considered one of the most prestigious awards in science, engineering, and technology, at least in the US and in some cases worldwide. Among the many others that Afshin already mentioned, I won't go through them, D. Brian Spalding from England was one of the originators of computational fluid dynamics. We gave the award to him in mechanical engineering in 2010. And more recently, Adrian Bajan of Duke University, the originator of constructal theory, received it last year. So truly outstanding major contributors to the advancement of science, engineering, and technology in the world. And as it was already said, is the oldest continuous running awards program in science, engineering, and technology. But what I did want to say is that Villanova University was founded about 20 years after the awards program in 1842. And it's committed to, in quote, engaging hearts and minds of students, faculty, researchers with academic excellence, a strong sense of community, personal attention, service to others, and a foundation for lifelong success. It sounds like it came out of a book, but it didn't. This engaging hearts and minds comes really from the teachings of St. Augustine, who was the most significant Christian thinker after St. Paul in the early ages of the Catholic Church around 300 AD. And it's a foundational element of what we do at Villanova as part of the Augustinian education. It's taken very seriously in our strategic thinking and all of our academic discussions. So if one looks for commonality between the mission of Villanova and the writings of Benjamin Franklin, we're not surprised at all that it turns out that Franklin fully supported the idea of service to others. He was a big proponent of that. So in a slightly condensed form, here is what he said about it. For my own part, when I employed in serving others, I did not look upon myself as conferring favors, but as paying debts. I have received much kindness from men and God, to whom I shall never have the opportunity of making the least direct return. For I do not think that thanks and compliments, though repeated weekly, can discharge our real obligations to each other, and much less to those of our Creator. So it's very satisfying to see the connection between Villanova and the namesake of the Benjamin Franklin medals, one of which to Professor Jablanovich we come here today to acknowledge and to celebrate his outstanding technical achievements. I wish you all a very inspiring symposium.
Thank you, Jerry. I'd like to invite Dr. Darrell Williams. If I go back. Dr. Darrell Williams is the
Got this? All right, can you hear me? Good. So good morning. So as mentioned, I'm the Senior Vice President of Science and Education at the Franklin Institute, and it's my pleasure to welcome all of you here this morning to this particular program, which is in honor of Dr. Eli Yalbinovich, who's our 2019 recipient of the Benjamin Franklin Medal in Electrical Engineering. So as also mentioned too, and I guess I got scooped, but they say if you say something 3 times, then that means you'll retain it. So I'll say it again, and this will hopefully be this is the 3rd time. But since 1824, The Franklin Institute has honored more than 2,000 scientists, engineers, inventors, and entrepreneurs for their most groundbreaking achievements of the past 2 centuries. Our laureates have truly changed the world with their remarkable work, and Eli Yablonovich is no exception. Each spring, a new class of Franklin Institute laureates comes together in Philadelphia to participate in a week-long celebration of scientific achievement. During this time, they engage learners of all ages and levels in a broad range of educational experiences that best represent the Institute's mission to inspire a passion for learning about science and technology. In fact, yesterday, Dr. Yablonovich got a taste of what the Franklin Institute is all about when he demonstrated some of the aspects of his work to our museum visitors. The crowning event of the week will take place tomorrow night, when our laureates will accept their gold medals at a grand ceremony before an audience of more than 800 guests. This symposium today is an important part of our Awards Week programming, and on behalf of the Institute, I, of course, would like to thank Drexel, who has been a longtime collaborator in many exciting initiatives, including the Philadelphia Science Festival, which will be taking place later this month. And we are grateful for the partnership, as well as for hosting us here today. We are also grateful for the support of Villanova and the IEEE Philadelphia section for their support of what I'm sure will be a fascinating program. I would also like to thank Professor Afshin Dariush of Drexel University and Professor Ahmad Hufar of Villanova for their special role in organizing this program, and also as Dr. Yablonovich's laureate sponsors. They are the members of the Institute's Committee of Science and the Arts who, along with other members of the Electrical Engineering Subcommittee, which includes others here today, lead the investigation of Dr. Yablonovich's work and convince the full committee that he is worthy of his recognition, which of course I'm sure is did not take a lot of convincing, as we all know. We are extremely grateful to our Awards Week sponsor, FS Investments, which has made our awards programming possible, and for Bank of America, the longtime presenting sponsor of the awards ceremony, which is taking place tomorrow night. You can watch Dr. Yablonovich receive his medal live on our Facebook page or on our website, www.fi.edu. Please tune in to the live stream tomorrow, which begins at 7 p.m. And so now I'm going to take this opportunity to share a video which encapsulates the rich history of the Franklin Institute and shows some of the giants of science history that Dr. Yablonovich joins as a new member of the Franklin Institute laureates. Yeah, let's see here.
PowerPoint presentation.
Oh.
Okay, so
I think I looked it up. There you go.
When, in the course of human events, a spark of inspiration sets the world ablaze with the fires of enlightenment and puts us firmly afoot on the way of progress, connecting us to one another in ways that elevate all of humankind to equal stations in which to pursue understanding. A decent respect for innovation requires that we recognize those who so affect our receding horizons, using only that to which the laws of nature entitle them, and declare that these inspired few are the architects of our future, and their insights the foundation upon which humankind distinguishes itself from all others. And with this, we hold that truth is not always self-evident, that it sometimes lies deep below the surface, and that the deserving are those who dare to seek it there, and then return to spread the word and say that with a single moment of inspiration, we have truly moved forward. This is our declaration of progress, a legacy spanning nearly 2 centuries. The Franklin Institute Awards, the spirit of independence, emanates from Philadelphia.
Thank you, Daryl. Now we are moving on the technical side of things. What I'd like to introduce is how our cluster and Professor Hurfa and I ended up with the nomination, and also the fact that how we felt the importance of the photonic bandgap engineering and electromagnetic bandgap engineering in terms of the impactful practical applications, and how our daily lives has been already influenced by it. I didn't know, but some of the innovations of Professor Jablonovich is in the antennas of the iPhone. Professor Jablonovich is a James and Catherine Lau Chair Professor, which is quite an honor coming from Professor Cam Lau, and the fact that this recognition is bestowed to Professor Jablonovich shows in many respects the importance of this recognition. He's also director of the NSF Center for Energy Efficient since 2010, and a very important center at University of California in Berkeley, a senior faculty scientist at the Lawrence Berkeley National Laboratory and Kavli Energy Nanosciences Institute since 2007, Northrop Grumman Optoelectronics Chair at UCLA before moving to UC Berkeley, Director of the Solid State Physics Research, Bell Corps from 1984 to 1993, and many of us are very much looked into the Bell Labs and all the major contribution that it had made till their separation, which pushed, in my opinion, the US science and technology in a backward direction. But it unleashed enormous intellectual capacity in various universities, and Professor Eli Jablonovich is another representation of it. Director of the Solid State Physics Research in Bell Corps, as I mentioned, Exxon Research Center, Harvard University Associate Professor in 1979, Bell Telephone Laboratory from 72 to 74, Teaching Fellow at Harvard 71 and 72, and Harvard University Masters as well as the PhD in 69 and 72 respectively, and also a graduate of McGill University in Montreal, which my daughter, who is also a graduate, she was very much enthused by it. Professor Jablonovich is highly distinguished, and I have listed some of the awards that he has received. One of them is the Frederick Ives Medal, and Frederick Ives is a recipient of the Franklin Medal for the new approach of diffraction grading, which has influenced so many different aspects of science and field. The other importance is the member of the National Academy of Sciences, National Academy of Engineering, National Academy of Arts and Sciences, as well as National Academy of Inventors. He has received a number of awards. One of the important distinctions is being the foreign member of the Royal Society of London since 2013. The key aspect that influenced Ahmed and I's opinion significantly was the interest that he had in developing this new concept of the photonic crystal, which is very appropriately also called Yablonnovites. In particular, his paper, Inhibited Spontaneous Emission in Solid-State Physics and Electronics, PhysRev Letters in 1987, up to now has received over 17,000 citations, and it's the second highest citation in PhysRev Review Letters. Professor Dowling indicated very early on, since 1988, a record of papers that they were being published, and he kept it on a website. But the growth was so fast, doubling every 2 years in the field of the photonic crystal, and the intellectual contribution was significant, that he stopped following it through because it went beyond the academic responsibility of one person. Professor Yablonovich has 17 patents, and one single invention of his patent on optical reflector structures, device, method, and fabrication and communication is a very comprehensive patent that has received enormous amount of accolades. He founded a number of small companies, not only being academician and a teacher, but also innovator and also an entrepreneur. He has over 57,880 citations. This is as of last night that I added that updated information. And he has over 14,968 since 2014. Numbers doesn't mean anything, because sometimes you are not being recognized during your time, but you will be appreciated later. But it is good to know that you are also being appreciated in the current time. And as a result of it, the scientific citation reads, for the pioneering work on conceptualization and experimental activity. This is the emphasis that distinguishes Professor Yablonovich from Professor John. And demonstration of the photonic and electromagnetic bandgap engineering for the confinement of electromagnetic waves with applications in photonics, microwave antennas, and structure. And we are going to focus on various aspects related to that. And I'm going to do a dual presentation. I would go through the photonics, and Ahmed is going to go through the electromagnetics. And so let me explain to you what that is. If we look at the light cone, which identifies that you cannot go faster than the speed of light, thanks to the principle that has been established for quite some time, and we all accept it. But you can definitely slow it down. And the way that it's being slowed down is by what we call index of refraction. And some of the legacies that are listed in here are related to the material characterization and how we have established this understanding since the beginning of the 20th century. So for the layman, if we look at the car in Germany driving in Autobahn, you have a faster speed limit. And if you're in I-76, you have a limitation. That is the reality. And what has been known in terms of the Bloch and Floquet theorem is the fact that you would be able to have in periodic structures with the periodicity of a field representation that shows a traveling wave with this periodic feature built into it. And this has been established in early 20th century. That what made the innovation of the semiconductor physics, which brought us all kind of knowledge of the transistors as well as a variety of electronics, and what was the major innovation that was made first by Baikov and then pushed through by both Professor Jablonovich and also Rajiv John, is the fact that you can also implement it in electromagnetics. And some of the features in terms of what we call Brillouin zones. And to understand how it works is primarily the fact that if you have number of barriers in your system, you would be able to find a path, and that's an electron that can easily pass through various sections. So this is the concept of the photonic band gap, in particular photonic crystal engineering. And it has a lot of important applications in terms of the nonlinear effect. Company NKT Technology in Denmark is using this photonic crystal to make a nonlinear optics base for coherent tomography application by extending the input pump optical signal to a shorter wavelength using the doubling and tripling effect. And this important feature not only is nonlinear effect, but also the dispersive effect, which can be used extensively for a number of other applications. One application that my group has been very much interested in is the phase modulators as well as the Mach-Zehnder modulator, which is the optical modulators that are being used as a backbone of internet, 40 gigabits per second, and now we are pushing it at 120 gigabits per second, using another important innovation that Professor Jablonovich has is in it, and that is the silicon photonics. The photonic crystal is a very important feature because it blocks the transmission of energy at certain wavelengths, and it allows the transmission of the wave in a behavior which resembles the forbidden regions or the band gap regions of semiconductor material. To understand it, like any other engineering problem, we have to have analytical tools, and there are two tools that are very popular. One is the analytical, which establishes the basic foundational understanding, and then you have the numerical technique. And in particular, if you have a stack of dielectric, high dielectric constant, and Professor Jablonovich identified that it is larger than 2, and air, you would be able to create a periodic behavior, and we can understand it by looking at one of these unit cells, and you would be able to show it in terms of the complex propagation constant gamma, as well as the characteristic admittance of the unit cell as a transmission line. And if YF is imaginary, that means that the wave is being reflected. And if YF is real, that means that the wave is being transmitted through. You can also use the numerical technique, optical FTDD, to create a unit cell. And I don't bore you with the detail of the analytical aspect, but here's the behavior that you have certain regions that the attenuation constant, gamma complex, alpha going to infinity, that's the stop band, alpha going to 0, ideally no loss. And then you will see with this simple modeling, you would be able to show pass band and stop band. And here is another view of it in terms of the reflection coefficient and transmission. And you will see that the transmission coefficient approaching 1, that's passing through. And when it is 0, that means that it is in a stop band. And here is another view of it. And you can apply it for dielectric structures in here. And here is the example of the stacked dielectric, once again showing the first Brillouin zone and the band gap region, and the second one and third one, and there are many of them that they appear. And in our application, we are looking at the short optical pulses, so we are very much interested in a pulse of the 100 femtosecond. And what we are interested in is this behavior that is going to be over a broad optical wavelength. And we use the nonlinearity and the slowness of the wave in this region, and this is zoomed in, that we wanted to accomplish over a 40 nanometer optical bandwidth. And here is the structure, and the key aspect is, without the photonic crystal, the amount of voltage required to have 180 degree of phase shift over a centimeter long is about 7 volts. Voltage squared is the power, and we are very much energy conscious. Green energy is really the key aspect, and in this topology that we are looking at with the photonic crystal, the innovation that Professor Jablonowicz has made, we reduce it by a factor of 2. So that is a factor of 4 in terms of the power in this regard. There are many groups that they have used different topologies, and this is one from INO. And here is another topology, which also Professor Jablonowicz very early on identified based on the analogy to the semiconductor material. In fact, having defect, like here is the order, and all of a sudden you don't have that order in here, and it introduces energy states in the same manner that in a semiconductor material, when you dope it with the homogeneous material in there, like doping silicon in gallium arsenide, replacing the gallium to make it a donor atom, or replacing the arsenic to make it an acceptor atom. So you would be able to create this kind of feature. And this is one aspect that it shows in the band gap region. You would be able to have an odd and even modes, and here is the even modes, and here is the odd mode, and this is how the wave could propagate. You can take this from one-dimensional to two-dimensional and three-dimensional, and you're going to hear from a number of speakers in terms of the dimensionality, how you would be able to do a lot of interesting things. And Professor Nader Engeta is going to bring some of those features into the discussion. So I wanted to give the floor to Professor Hurfar.
All right, good morning, everyone. So what I would like to do today is, in this part of the introduction to this seminar, is show you when we go from PBG, photonic band gap, to electromagnetic band gap. First of all, why we need that, and secondly, what kind of magics we can do with that. So we all know that there are challenges in designing low-profile antennas above conducting surfaces, and there are many platforms that they have conducting surfaces. In general, planar and printed antennas have poor radiation characteristics when they are very close proximity to conducting and metallic surfaces. And also, you have the problem of propagation of surface waves. If you have a single antenna, the surface waves, propagate, and when they hit a discontinuity, say the edge of a ground plane or truncated substrate, they're going to make ripples in the radiation pattern. They're going to increase your side lobe, and also they bring down your efficiency, and also increase the coupling when you have printed antennas in an array. The other thing happens when you have phased arrays. Because of the propagation of surface waves, at certain angles, when you try to direct the beam, the power is not going out, and at that angle, you're going to have a blind scan angle that you cannot direct your beam. So why antennas, they have poor radiation characteristic when they are above conducting surfaces? So if we go to the ideal case, perfect electric conductor, if I have a horizontal dipole, and very close proximity to this ground plane. We know by image theory, this generates an image in the opposite direction. Obviously, if I bring this closer to the ground, image and the dipole itself, they cancel out. They have when we have poor radiation characteristics. On the other hand, if we have a perfect magnetic ground, in that case, the reflection coefficient is going to be +1. So actually, the image current is going to be in the same direction as the dipole itself. You are going to have enhanced radiation performance. But the problem is that we don't have PMC in nature. So we are trying to, people have done for many years, they have been trying to synthesize materials or surfaces that they behave like PMC. And they are called artificial magnetic conductors and high impedance surfaces. So actually, people have known for many decades that if you have a corrugated surface, you could generate a high impedance surface. But the problem is this is very bulky, quarter wavelengths. And what Professor Jablonovich and his then PhD student Dan Steven Piper and their colleagues did was introduce a very simple structure, which is now known as mushroom-like surface. And I discuss this in a minute in more detail. And they had this seminal paper which motivated actually many researchers around the world. And many groups came up with other surfaces, with and without vias. This surface has a via. And basically this paper that has over nearly 4,000 citations kick-started what we know right now as high impedance surfaces and electromagnetic band gap engineering. So why you have high impedance surface? So if we look at the mushroom-like structure, we can model this by an CL circuit. So if I form the equivalent impedance, when it goes to resonance, denominator here goes to 0, impedance goes very high, theoretically goes to infinite. And if you have a normal plane wave incident coming and hitting that surface and you calculate the reflection coefficient, magnitude, assuming there are no losses, is going to be 1, whereas the phase goes through a transition. You go from PEC, 180 degrees, through 0, which is a perfect PMC, and again to PEC. Of course, in reality, because of losses and other effects, you're going to have a transition like this. But exactly at this point, you have a perfect PMC. So the paper by Professor Jablonovich in IEEE transaction on MTT not only introduced the high impedance surface, which was low profile, but also showed that within a band, no surface wave can propagate of either polarization. And we are showing it here, and this is the surface, the so-called mushroom-like structure. So exactly at this point, you have a PMC behavior, so high impedance surface behavior, and at the same time, you prevent propagation of surface wave. Now, this is very important because it has many important applications. Highly efficient, low-profile antenna elements and arrays, mitigating array scan blindness, and also reducing co-site interference. When you have antennas with different functionality sharing the same ground plane, and they could interfere, so you can reduce that. And I'll go and show you some of those examples, how you can do that. So in general, high impedance surface and electromagnetic band gap engineering in the last 20 years or so have resulted in many innovative antenna and microwave design, and especially in antennas. First of all, you could have enhanced design of planar antennas. You could have novel electrically small antennas, and I'll talk about this in a minute in more detail. You could reduce scan blindness. You could make cell phones safer because you can reduce this specific absorption rate in human head. You can design actually electrically thin radar absorbers. You can enhance design of RFID tags when you want to tag conducting structures. Many applications in microwave, phase shifters, cavities, and components. And also, recently, people have used this concept in massive MIMOs in order to reduce correlation in MIMO antennas when you have multi-beams. So let me just briefly go with some of these applications, not all. First of all, reducing mutual coupling. This was one of the papers by Dr. Ramaswamy's group that used this concept, developed by Professor Jablanovic. And you have two microstrip antennas, and you have an EBG in between. So we see here the coupling, which is shown with S12 with EBG and no EBG. And in this case, you are reducing the coupling by about 5 to 10 dB. If we go to an array, this is a 3x4 element array. And again, we have the EBG layers here. If we don't use the EBG, we have a scan blindness here. And in that case, reflection coefficient goes to 1 or 0 dB without EBG. But with the presence of EBG, we mitigate the scan blindness, no scan blindness, and also the reflection coefficient goes down. Now, a different variation of high impedance surfaces is called reactive impedance surface, or RIS, and Professor Sarabandi is going to talk more about it. He has done many innovative work in that regard, pioneering work. And basically, surface impedance of a reactive surface impedance ideally is purely reactive. And you can design this such that you can tune it to any surface from PEC to PMC. And that's the important thing. So this is one example, and it's in this paper, that reducing size of the microstrip patch. And you can see the size has been significantly reduced, and actually bandwidth has increased. However, here, because of larger inclusion size or cell size using, still the surface is much larger than the patch itself. But more recently, Dr. Sarabandi's group published this paper that show, this is at 400 megahertz, and reduced the size of the RIS, and this is with an optimized patch, and the whole thing occupies this volume. Albeit, I think he's going to talk about it, slightly reduced gain. But you can see this is really remarkable using this RIS surface. Now, we know a concept called Salisbury shield, and basically you put absorbing screen about quarter wavelengths from the surface of the conducting ground plane. In that case, electric field is maximum there. So if you have put a lossy substrate here, I can suck the energy and actually absorb the energy, and I have basically a radar absorber. But this requires a quarter wavelengths. But you can use actually a high impedance surface. And in this case, it's a fractal surface. This is a work we did together with Dr. Engedwa many years ago. And you can have doing the same thing with a surface which is only a fraction of wavelengths thick. And actually, it works. This is the experimental result when you have a conducting plate. Without the surface and with the surface, as you can see, RCS reduced by over 30 dB. And finally, in this paper, this is actually a PhD thesis recently in 2016 in Germany, and they used an EBG below a printed inverted F antenna. And they were able to reduce, and these are measured results, reduce the SAR, specific absorption rate, by 55% inside the human phantom. So these are not theoretical. Actually, they measured this. So with that introduction, when we were trying to convince the Committee on Arts and Science of Professor Jablanovic's case, we received numerous letters. And I want to show you the excerpts from some of the letters, and some of the two people couldn't be here, as Afshin said. We are going to have short congratulatory videos that we are going to play. But let me go to few of the letters and excerpt from those letters. The first one is from Professor John Pendry. He wrote, actually a 3-page letter. And these are some highlights. He said, in 1990, John Maddox, the editor of Nature, wrote, if only it were possible to make dielectric materials in which electromagnetic waves cannot propagate at certain frequency, all kind of almost magical things would be possible. And Maddox was writing this in response to proposal by Jablonowicz, who is the prime initiator of the field of photonic crystals. Also, he wrote that Jablonowicz has been a leader in optoelectronic science and materials engineering, whose achievement span both science, and this is important, as well as the practical application of the science. These are some of the comments in the letter by Professor Connie Chang-Kaznian, a colleague of Professor Jablonowicz from University of California, Berkeley. Professor Jablonowicz has been a leader in optoelectronic science and engineering, and also he was the first to demonstrate successful photonic band gap structure. Today, there are thousands of publications per year on photonic crystal in many areas of science, technology, and medicine. And she goes on to say that I cannot think of another individual more deserving of the Benjamin Franklin Medal in electrical engineering. Professor Tatsu Ito, former colleague at UCLA. Eli is a visionary researcher with deep understanding of physical phenomena in both natural and artificial materials such as PBG. Not only has he discovered and developed a new scientific research topic, but a new scientific community has been formed. And also, this is from Professor Andrea Alou, University of Texas at Austin. Professor Jablonowicz is considered the father of photonic crystals, a field that has dominated the research in optics and beyond for the last 3 decades. And he goes on to say that this on its own is a fundamental contribution, which has not only revolutionized the field of optical physics, but has also led to many important new technological advances, including photonic crystal fibers and the electromagnetic bandgap materials and metamaterials. So there were 2 people that we invited to be here. Unfortunately, because of the other work commitment, couldn't be here. One is Professor Stefano Macci. I'm not going to read one of the comments in his letter, but I'm going to play a video that he sent us.
Dear Professor Jablonowicz, I apologize for not being there to personally congratulate with you for this prestigious Benjamin Franklin Medal. For who is not aware about your scientific contributions and their impact on the electromagnetic community, let me say that Professor Jablonowicz is considered one of the greatest scientists of our time. He is the inventor of the concept of photonic banded crystals, and his paper entitled Inhibited Spontaneous Emission in Solid-State Physics and Electronics, published in 1987 on Physical Review Letters, has opened the new dimensions in photonics, and it has been cited more than 70,000 times. It is one of the most cited journal papers ever published in solid-state physics and electronics. The concept of PBG implies the possibility to have light propagation in the channel of defects in the PBG materials and resonances in extremely miniaturized cavities, and has opened a new path of research in optics and electronics. In addition to pioneering photonic bandgap crystals, he was one of the first that recognized that a strained quantum well laser has a reduced threshold current. This concept has had an extraordinary impact in the semiconductor laser industry. The photonic banded crystal concept has also had a strong impact in microwave and antenna community, since it rendered it possible to conceive the electromagnetic bandgap surfaces where surface wave cannot propagate in a certain range of frequency. This concept was the precursor of metasurface concept of today. His paper, High Impedance Electromagnetic Surface with a Forbidden Frequency Band, based on the PhD work of Dan Sieben-Piper and published in IEEE Transaction and Microwave Theory and Techniques in 1999, got about 4,000 citations and is one of the most cited papers in microwave engineering. In that paper, a mesh surface was introduced that has been used in a large number of microwave antenna applications, like, for instance, low-side low monopole antennas, non-zero impedance horizontal dipole extremely close to the ground plane, and patch array antennas with low coupling among elements. Mesh surfaces, besides inhibiting the propagation of surface wave in a certain bandwidth, also behaves like a perfectly magnetic surface for space wave impinging close to the normal direction, allowing for quasi-TEM propagation in a rectangular waveguides. Diarelli, you are one of the most prominent scientists in physics and electromagnetism. I'm proud to have had the opportunity to support you for this prestigious Benjamin Franklin Medal in Electrical Engineering. Good prosecution of the event to everybody.
And also, we received a video from Professor Siebenpiper.
Hi, this is Dan Siebenpiper from UC San Diego. Hi, Eli. I wish I could be there in person. Since I can't, they asked me to send in a short video of some of my memories of what it was like to be a graduate student with you. There are really three things that come to mind. The first was your ability to see things before anyone else could. So we would be working on a topic that was not really on most people's radar, and then sure enough, a couple of years later, it would become a hot topic. How you could find these ideas and start coming up with solutions before anyone else was talking about things was really quite amazing. The second was your ability to come up with concepts that are far outside the mainstream. So things like epitaxial liftoff, for example, or your natural lithography for making random textures for LEDs and solar cells, or obviously photonic crystals, things that other people just wouldn't think of. Then the third thing was your ability to express these ideas in ways that people can understand, regular people can understand. This is something that's sadly missing from physics today. The ability to express concepts, complicated concepts, in plain language. So, for example, I remember you would always have these photonic crystal samples or prototypes in your pocket when you're going to a talk or a presentation, and you would lay them down on the ViewGraph projector. This is when we still use ViewGraph projectors, and you would tilt them to different angles so people could see the light passing through them in different ways to get an idea of the 3D nature of these things. So these are some of the things that I learned from you that I think are very important. The ability to think of things that are outside the mainstream, and then to take complicated ideas and express them in ways that people can understand. That's important for marketing, it's important for explaining your ideas, it's important for everything, really. So I'd like to say thank you for all of those things, and I'd also like to say congratulations on winning the Franklin Award.
Thank you very much, and I'd like to invite Professor Nader Engeta, who is going to make a presentation on metamaterial machines and 4D metastructures. The bio of various speakers are listed in the booklet, so I would go directly to the presentation for you, Nader. Almost set.
Can I use also a slide? Thank you very much, Afshin. It's a great pleasure and honor for me to be here, and I'd like to take this opportunity to congratulate my friend, Professor Yablanovic, for this great occasion of receiving the 2019 Franklin Medal in Electrical Engineering. It's most well-deserved. and it's a wonderful occasion that we are sharing this joyful moment today. And I'd like to thank my friends Afshin and Ahmed for organizing this symposium and for giving us a chance to get together and celebrate this wonderful moment. When Afshin and Ahmed asked me to give a talk in this session, I was thinking to talk about one of the research projects that's going on in my group that I know Eli would enjoy. So I decided to talk about what we call metamaterial machine, and can we have structure, material structure, that will actually work as computing machine when you send a wave through it. So because that concept relates to metamaterial, I'm going to present few slides as the introduction to the concept of metamaterial, particularly for those who may be less familiar with the concept, and then get to the main topic in a second. Well, all of this really goes back to the issue of light-matter interaction. And in fact, the photonic crystal that Eli pioneered really goes back to how wave interacts with material. So when we deal with light-matter interaction, we all know that's governed by the laws of electrodynamics, both classical as well as quantum electrodynamics. And we usually like to parameterize this interaction by certain parameter values that all of you are familiar with, and permittivity, permeability, conductivity, and so on and so forth. Now, in nature, the materials that we have available from periodic structures and the derivative of periodic structures actually exhibits certain range of values for these parameters. But the concept of metamaterial actually enables us to go beyond these range of values to actually make and construct materials that would exhibit different range of values for these parameters, obviously physically realizable. And the concept actually forms like this, that you start with the host medium. Let me actually use this one. You start with the host medium, and you embed them with the man-made inclusions. And these man-made inclusions, by the way, can have various different parameters. And when you send the wave through this, the wave is going to induce electric and or magnetic dipole moments in this structure, and those dipoles re-radiate. For the observer sitting outside and looking at this whole ensemble, an observer would see a homogenized values for those parameters. So effectively, you can engineer effective permittivity, effective permeability, and effective index of refraction in the range of values you like to have, but not just what the nature has given us. Now, why this concept is powerful is because you can actually have several knobs to turn. You can choose the composition of these inclusions, the alignment and arrangement of this. For example, photonic crystal are the ones that has a periodic structure of that, but you can have other form of arrangement. The density of these inclusions, obviously the host materials, but last but not least, also the geometry and the shape of this inclusion. And that's one of the actually interesting points in the past several years, that the nanotechnology and nanoscience would allow us to actually come out with a structure that would be a sub-wavelength compared to wavelength of light. And because of this ability, by the way, in the past several years, there have been a lot of activities in the metamaterial. Here I'm just showing just a sample of different metamaterials that different groups have made all over the world. And this by no means is an exhaustive list. I can show you pages and pages of examples of different type of metamaterials, some of which actually my colleagues Afshin and Ahmed showed, and you will see also from Kamal's talk later on. Now, because you have the ability to engineer the parameters, then several different applications, by the way, have been explored over the years. Concept of cloaking, superlens and hyperlens, deeply sub-wavelength cavities, transformation optics, electrically small antennas, near zero index optics, optical metatronics or optical nanocircuitries, and the two-dimensional version of metamaterial known as metasurfaces. Now, in my group, we are interested to see how we can go to the next stage, to actually look at some extreme scenarios of these light-matter interactions. And today, I'm going to talk about only one of the several research programs that we have in the group, and this is a concept that I would like to call metamaterial machine. And this actually started by posing the following questions. Now that we have the ability to design materials to actually do interesting things with waves, and to actually control and manipulate waves to do some unusual functionalities, a question comes up that can we actually use the concept of metamaterial and to see an interesting connection with artificial intelligence or with computation. And in order to focus that concept, let's look at the subset of this. And we pose the following questions. Can concept of metamaterial help us to do informatics? In other words, can we actually use the material to do information processing? And again, to concentrate more focus on that, we'll look at one question. And the question that by end of my talk, you see that that actually will be possible. And the question we pose is the following. Can metamaterial solve equations? In other words, could we design a metamaterial that when you send a wave through it, by the time the wave comes out, you would have a solution to an integral equations? Essentially, the so-called the analog computation, but now can happen with waves and can happen at the nanoscale. So what is our goal? Our goal is the following. Imagine that you would like to design a structure with a combination of sub-elements over here. And the question is, how do we actually decide on the shape, size, and material of this sub-element such that when you send an arbitrary wave through this, when the wave comes out, the output would be the desired function you would like to have for the arbitrary input. For example, if you would send an input to an integral equation, what should this distribution be? Then the output would be solution to your integral equations. So, in order to get to the main question, we decided to look at some of the simpler problems first. But before even I show you what we have done, what is the simplest and oldest structure that actually would do information processing for you? And we use that every day. A simple lens. A simple convex lens would do Fourier transforming for you. And we all know that, and of course, that's the foundation behind all the imaging technology that we have there. But then we ask ourselves this question, okay, you know, in a regular simple lens that we have, for example, optical axis going through this, and you put an object over here, you can find the Fourier transform of that there with light. Can we do other transformation? Mathematics is full of so many other transformation, Hankel transform, Mellon transform. Of course, the simple lens would give us Fourier transform, but now with the ability of designing material and shape, could we actually design an optical structure that would do other transforms? For example, could we actually design a structure that would have a broken optical axis? Now, what do I mean by that? Imagine we would like to actually have a material distribution over here such that it will work as a lens, but not as a regular lens, as a lens that has a broken optical axis. By that I mean this, that when you send a wave over here, you would like that the focal point be that way. Now, why are we interested in that? There's an interesting set of applications we are looking at that. For example, could this structure be an interesting alternative to the confocal microscopy? This is an ongoing work that we are doing right now in my group. Now, the question is, how are we going to do that? What kind of material do we have there? Now, you might say, well, a combination of regular lens and mirror can do that. We would like to have as simple as possible one single structure that would do that. So we decided to use, optimization, inverse design. By the way, Eli was one of the pioneer people on the work of inverse design. And using the optimization and inverse design, we came up with this distribution. Now, this is very interesting, by the way. This consists basically on only two materials. The blue region is just air, and the red region is a single dielectric with a dielectric constant 1.5. Now, we didn't want to build this. This was just to show that the inverse design can do that. Now, when we want to build that, as you will see later on in my talk, of course, we have to put some constraint on the fabrication limit as well. So if we actually illuminate this with a wave, simulation shows that indeed it gives you an actually interesting, focusing with the broken optical axis. And if the goal is to actually have an imaging system that the image of that would not necessarily be parallel like a regular lens, that we can do that too. We call it the oblique imaging system. That steps towards our goal, towards replacing confocal microscopy with this technique. So take a look at this. This structure that I showed you before, we did another inverse design over here. And you notice quite interestingly that this is not periodic at all. So when you actually go beyond a periodic structure to make it non-periodic, the parameter space opens up. You have many degrees of freedom, and as a result, you can actually take advantage of those degrees of freedom to do that. And that's what the inverse design would allow you to do that. Mathematics becomes much harder, but the inverse design would help us to get to the point. And indeed, you can see that simulation shows that you can have image of an object over here, not necessarily in the parallel image of that, but any direction you would like to have. And I mentioned about Hankel transform. So we decided to see whether we can design a structure that would do Hankel transform instead of Fourier transform. Indeed, that's also possible. And by the way, if you look at this design, at first look, you would say this looks like a periodic checkerboard. But actually, this system is not periodic. In fact, if you take a look at it, you see there are interesting non-periodicity happens over there. And when you do the axial symmetry rotation of that, Hankel transform can turn the Gaussian Bessel function input into a delta function. And indeed, this simulation shows that it works like this. So we don't need to actually limit ourselves with what nature has given us as just a convex structure of a glass, as a regular lens that would do Fourier transforming. Now we can actually design a system that would do the transform you like to have. Now, with this background, let's get to the main goal we have. Could we use metamaterial for informatics? So, of course, we get inspiration from electronics, the same way that Eli inspiration for the photonic crystal comes from semiconductor, band gap structures. So we know, by the way, that if you have lumped circuit element and put them together, you can have electronic processor. And we always, use that. So we said, what would happen if we have a structure like nanoparticles that represents our form of lumped circuit element in light? Can we put them together in order to do interesting processing? About 4 years ago, by the way, we proposed the idea that we can design a metamaterial that when you send a monochromatic wave with an arbitrary profile through this, by the time the wave comes out, the profile of that will change, of course. But the shape of the profile will be the mathematical operation you like to have on the shape of the input. In this particular case, for example, we design a set of metamaterial that can take the derivative. So in other words, material can become calculus. You can have a photonic calculus. You can design a material that would take the derivative for you, that would take the integral for you, that would take the convolution for you. As one interesting low-hanging fruit application, we actually design a set of metamaterial over here that when the wave goes through it, it will actually take the second derivative for you. The second derivative is in space. Now, why are we interested in the second derivative? Because second derivative is a very interesting operator for edge detection. And that would be a very interesting technique in image processing. Now, the ordinary image processor that we currently use in our computer, of course, is the digital system. You have to digitize that, and then you have to raster scan to find the separation. This system is an entirely analog system. An entirely analog system that the wave goes through the system at the same time. So you can actually have the image processing in the very massively parallel system as an analog system. Shortly after we published this paper, several other groups, show that indeed this concept is possible by actually designing metasurfaces that would take the derivative. But now we put actually a more ambitious goal for ourselves. Now what we'd like to do is that to actually solve equations. Now that we know we can actually take the derivative, take the integral, why not go to the next step? To actually design a material that can solve integral equations for us. Now, why did we decide to choose integral equations? The answer is obvious. Any field of science and engineering you pick, you have to deal with integral equations. And integral equations, unlike the differential equations, they're not that easy to solve analytically. And the way it's solved these days is that you have to discretize and you have to invert the matrix. So we ask ourselves, why not use the parallelism of light in order to actually do the inversion of a matrix and try to find, the solution to an integral equation? Essentially, what we are saying is that we are resurrecting the idea of analog computer. Now, many people in the audience are very young, but some of us who have been around in a few more years remember that in 1960s, 1970s, we had analog computers. But analog computers of those days were bulky, were lossy, were power hungry, as you can see there. And one of the reasons that digital computer became so successful over analog computer is the fact that the digital computers are programmable. And that's one of the things, by the way, by the end of my talk, I will address that it would be nice to actually have a metamaterial that would be programmable, that would be reconfigurable. And in that case, the concept of analog computation can become very, very powerful. Okay, how are we going to do that? First of all, we know how to design the structure that would give us that operator, that integral operator of your choice. Oh, one thing I forgot to mention, by the way. This, of course, as all of you know, is the Fredholm integral equation of the second kind. Particularly, I'd like to emphasize, to keep things as general as possible, I'm assuming that this kernel that we have over here is not y minus y prime argument. In other words, this is not a convolution. Because if it were, we could use the Fourier transform, and we don't want to do it. So intentionally, this kernel is not y minus y prime, and also the limit of integration is completely arbitrary. So it's not from minus infinity to plus infinity. So the goal is this, that for an integral equation of a given physical problem, kernel is known. For any arbitrary input to our metamaterial structure, we would like to see whether the output wave would be the solution to our integral equation. So we know how to design this, but this is not enough. We have to have a feedback system. And when you have a feedback system, you have a system that has your own eigensolution, and the eigensolution would be solution to this integral equation. Essentially, our vision is this, that you have a system that the wave can go feedback system over here with an arbitrary input coming in. This is the main part of the design that we have to design to have that particular kernel. And for any arbitrary input, we can have the output there. Okay. Right now, we are studying two platforms for this. One is using the inhomogeneous metamaterial, which I'm going to show you how we have done it and did an experiment on that. And another one, we are using a collection of Mach-Zehnder interferometers with interesting possibility of reconfigurability. In other words, bring the time into play, and we can have it a four-dimensional space, so to speak. Now, the first approach. The idea is to start with a material and try to find out what is the inhomogeneous distribution of permittivity of that in order to give you the kernel we want, okay? And then when we have that, then we have to introduce the feedback system to this. So essentially that becomes like a very, very sophisticated cavity whose eigensolution you engineer, not the natural cavity, but the cavity that you engineer to have the eigensolution of that particular kernel. And then you bring an arbitrary input over here using directional coupler, and then you get the output of that using another set of directional coupler. Essentially, that reminds us of a collection of ring resonator. So you might say this looks like a ring resonator, but actually it's not. Yes, there are actually n rings over there, but the crucial point is the coupling among them. And that particular metamaterial is the key to this aspect, because that determines the kernel of the integral equation. Okay, how are we going to do that? Let's start with an interesting example. For example, let me assume we start with this kernel. This kernel, we choose it arbitrarily. This doesn't represent any physical quantity for a moment. But the important thing is not y minus y prime. And as a first example, we decided to have a separable kernel, because of course we can also find analytically the answer to that. So we started using the concept of inverse design, objective first inverse design. And you start with a clean slate. Let's say you have 5 inputs, 5 output waveguides. And when we go through this inverse optimization design that we have, you get to this distribution of permittivity. Now, this is quite interesting. This distribution of permittivity shows that you should have the range of the parameter between 1 and 2. There was nothing magic about 2. We arbitrarily chose number 2 there. But this is not good for us, because this is a graded distribution. And if you want to have, for example, dielectric constant 1.3, you may not have that. What we had to do is to binarize this. In other words, to make it only with 2 materials only. Now, this is interesting. This consists of only 1 material and air. If you look at this distribution, the gray area is just air, and the black area is 1 single dielectric with permittivity 2. In other words, what that means is you get a block of dielectric and you make holes in them. And that's why I call it Swiss cheese. So it's like a Swiss cheese, but those holes and location of those are very important. So let's see what happens if we actually excite electromagnetic wave through this. Now, this is interesting. Again, it's completely non-periodic system. And in fact, for each excitation that you have at the input of this, you can go and look at the 5 complex numbers that you come at the output of that, and those actually would show you the kernel that we were looking for. But that's not it. This is not a solution to integral equation yet. We have to show that any arbitrary input to the system will give you a solution to your integral equation. So we created the feedback. Now, so imagine we have this feedback, and this is an arbitrary input we have over here. Please note that even though I say the input is 0, 0, 1, 0, 0, this is not a digital system. This is completely analog system. So what this means is that no excitation, just a CW excitation over here, no excitation, no excitation. Field goes through this. This is like those 5-ring resonator I mentioned to you, but this region couples them in a very important way. Now, what we need to do is to come over here and read the 5 complex numbers we have over here. And that is the solution to your integral equations. So this solid line is the result of simulation of this structure, real and imaginary part. And the dashed one is an exact solution we expect from this integral equation for that arbitrary input. So with this encouragement, we said, okay, why don't we change the input? So we change the input to something other arbitrary value over here. Obviously, the output will be different, but still very consistent to the exact output that we are expecting from that integral equation. So with that, we decided to do the experiment. And by the way, we did many other kernels, so I don't want to bore you with all those examples. So when we wanted to do experiment, we decided to do it in the microwave region, simply because the system is bigger first to do the proof of concept, and the next stage is to take it to the optical region. So in order to do that, we decided to really kill ourselves, meaning to choose a kernel that would be very general. So we decided to use this kernel. Now, this kernel doesn't represent any physical phenomena. We intentionally choose this kernel because it's very general. It's not y minus y prime. It's not separable. It's complex. And it's impossible to solve this integral equation using analytical expression. So when we applied the inverse design to that, we got this Swiss cheese for this. Because we were going to build this, we used this material Rexolite, which is a polystyrene, nice dielectric with the dielectric constant of 2.53, an imaginary part almost 0. And this structure, this is about 4 wavelengths by 8 wavelengths for this. Nothing magic about those numbers. That for the design, we chose this. And this is a simulation of what happens over here. Oh, one thing I forgot to mention. We needed feedback, as I mentioned. But as we were designing this for the experiment, another idea came to our head. And that is, rather than having a feedback external, we decided to have the feedback internally over here. So we used the 5 waveguides both as input and as an output system. So the footprint of the structure actually reduced to half of what we were expecting there. You notice how the wave goes over here and come out of this structure. So let's look at an arbitrary input of this. Remember, the arbitrary input we put is completely arbitrary. We have 90 degrees phase difference, 180 degrees phase difference. And so you put this field in with the proper magnitude and phase that you represent this input that you have there. Wave goes there, play around, coming out, and you look at the 5 complex number of the output that's coming out, and let's compare the results. 4 curves over here you see, 2 of them solid line, 1 of them real and imaginary part for the exact simulation we have done. And the thin lines are actually the exact solution we expect. So this we all did before we even started collecting the data in microwave, so we built it. And before we actually built this, one of the members of my group, Brian Edwards, did a fascinating job of actually simulating every single detail of this structure, even the thread of the screws we simulated, just to make sure that we get the result before even we start collecting the data. Then we build it. So this is a photograph of the structure we built over here. You notice that the 5 waveguides you have, there are 10 coaxial cable, 5 coaxial cable bring arbitrary input there. The other 5 coaxial cable actually take the output out. And these are experimental results. So 6 curves that you see over here, actually 7, this orange one is just the input. So input is 1, 0, 0, 0. The theory curve is the dashed one, real and imaginary part you see there. The simulation is the exact simulation of the structure that we have. The thin one, real and imaginary part, and experiment, real and imaginary part. All of them agree with what we expected to have. We change the input to another one, another one, another one. All the outputs agree with what we expected. So what is it in the future? What we are planning to do as our to-do list is now to bring this concept in the telecommunication wavelength, to use silicon photonics, bring the structure to the much smaller scale. Now remember that I mentioned to you that this is 4 wavelengths by 8 wavelengths. Bringing this in our next step to the silicon photonics, that means become few microns by few microns. So few microns by few microns can actually solve integral equations for you. And one of the plans we have is to actually have a collection of these. Each one of them would solve different class of integral equations. So the question is, can we have a massively parallel optical system that solve a coupled integral equation all together at the same time? And also I mentioned to you about the issue of reconfigurability. My goal is to make this reconfigurable because the programmability of that is very important. So one of the directions that we are thinking about is to actually look at the technology that we already available, that is rewritable CD. Rewritable CD actually use the GST, germanium antimonide telluride, to actually change the dielectric constant of the structure. Why not use that technology in order to print your micron-sized analog computer that are all coupled together? And one of the interesting points, many of you in the audience are familiar with the FPGA, Field Programmable Gate Array, which is one of the very interesting aspects of electronics and made powerful, the digital computer we have. One of my goals is to bring the concept of FPGA into metamaterial and make that programmable. And one of the things we are working in this right now is to actually look at the 3-dimensional version of this. This was the 2-dimensional of that. That brings me basically to the almost end of my talk, that we would like not only make this 3-dimensional, but also we would like to bring the temporal variation into play. So as this thing 2-dimensional, what would happen if the permittivity also changes with time? Now, we have a series of projects, by the way, on the temporal and the spatiotemporal metamaterial that we will talk about tomorrow in our regional meeting we have. Let me just show you a couple of slides and then I stop over here. So we decided to actually parallel with that, look at the collection of Mach-Zehnder interferometer. David Miller from Stanford had an interesting idea about Mach-Zehnder interferometer. He changed that slightly to create a 2-port system that by choosing only 2 phases, you can decide the magnitude and phase of the output system in any way you want. So we decided to actually look at the collection of this MZI to put them together in order to solve integral equation. In this case, this is actually a collection of Mach-Zehnder interferometer. It's not an inhomogeneous metamaterial. In fact, we showed this, that indeed is possible. You can choose any kernel you want, and by just choosing the phases of this Mach-Zehnder interferometer, you can actually solve this equation. So because those changes can be easily changed, this system would actually changes with time. So you have a 4-dimensional system over here. We designed the circuits. We're doing this in the RF domain, and we build it. And right now, this is work in progress. So we're collecting data on this to see what happens, and these are one of our early results, experimental result that we get it for the 2 of these boards. And indeed, you notice that you can cover the 360 degrees phases that you want and the amplitude you want. So as a result, this can actually evolve and solve integral equation as you actually change the integral equation there. We'll talk more about the 4-dimensional metamaterial tomorrow. So let me again congratulate my friend Eli for this wonderful award that he's receiving tomorrow night. And I would like to thank Afshin and Ahmed and all of you for being together celebrating our friends' success and accomplishment and this wonderful prize. And I want to thank you all very much. Thank you.
Thank you very much for a very illuminating presentation. We are at the time to take a coffee break. May I suggest rather than half an hour, we will do it in 15 minutes so we can catch up, okay? See you by 15 minutes to 11. May I have your attention? Could you please take your seats? We are going to start in a few minutes. Our next speaker is Dr. Alfredo Di Rossi from Thales Research and Technology from France. And please welcome Dr. Di Rossi, who is going to talk on photonic bandgap devices in integrated optical circuits. I mentioned one of the most important revolutions that we are going to see as the electronic revolution was in the 20th century. Photonic revolution will be in the 21st century, and you will see how this is going to be accomplished based on the presentation that Dr. Di Rossi is going to make. Please welcome Dr. Di Rossi.
So can you hear me? I hope you forgive me for my French and Italian accent, and you can still understand what I'm going to talk. So I'm really proud to be here and to have the opportunity to give my modest contribution and that of my colleagues to this big picture, which is Professor Jablanovich's invention of photonic crystals. And well, I will talk you more about a very specific aspect, that is how we try to turn photonic crystal into photonic device that can be integrated in photonic circuits. And I will insist a lot on this idea of integration because, in my opinion, that is really an important step forward because photonic crystal had unique functionalities. But it makes sense to have those functionality as something that you put on already established scheme that is going on very, very quickly nowadays. That is the photonic integration. So that is what is about my presentation. So first of all, 2 words about the company I work for. I'm from Thales. Thales is about so-called professional electronics. So it's about analog signals and analog electric signals. So why photonics? I mean, I'm going to talk to you about photonics. Well, the link is there. So you have an antenna. An antenna generates, this is mostly the business of Thales, antenna and microwave signals. This is going to generate electric signal, and then you need to analyze it. And what you do, you have to convert it into an electronic, in a digital numbers. And you have here some crucial aspect of this transformation that is analog to digital conversion. And it was pointed out mainly this pioneering work from a group on MIT that you can use photonics to make a much better conversion, more precise, faster, from analog electronics to digital electronics. And this is opening a new paradigm where you can see regard photonics as a front end between a communication layer that is often photonic and optical, and the computing that is still right now based on digital electronics. Maybe it is going to change. Oh, well, so this is the starting point. And then I want to show you this figure. Unfortunately, this quality has, well, this is our first photonic crystal made in Thales. And I want to show you the scale. This is alpha micron. And this, what you see here is a sub-wavelength. I mean, you need nanometer scale fabrication accuracy to make it work. And that was the achievement of my colleague, and at that time a PhD student, Sylvain Combré. He spent 3 years basically to achieve that. 3 years in fabrication, and then, we thought we can make something out of it. That was more than 10 years ago. And this is basically the line of my presentation. I want first to introduce you with all the difficulties and hurdles that the community had to face to move on. And then I will give you an example of one specific device, that is a photonic crystal laser as a device. And finally, go back to what you already heard about analog processing and see what we can do with this kind of photonic crystals. Okay, so you have seen that, and just to remember you what was the starting point. So the photonic crystal that had been invented by Professor Jablonowicz. And the first demonstration, however, was reminded it was in the microwave domain. And this is because scale favors fabrication of a microwave object rather than optical. And actually, the development of photonic crystal have been hampered, at least at the very beginning, for the difficulty of making sub-wavelength structure with the precision that you need. And actually, when we were start playing with that at my company, I must say that it was not easy to answer the boss saying, well, now when will you get a device working? So that was the starting point, and then it took some years to get to some convincing result, at least in our perspective. So I just want to remind you the fabrication process that we use. So it's based on early suggestion of Thomas Krauss that was long ago. He said, well, we can start using a planar process. The planar process is this one. So you have using electron beam patterning on a resist, then you use mask, you develop the mask like in photography, and then etch the semiconductor through with some process. So you have this kind of structure with this is a cross-cut, you see the holes, and then you remove a sacrificial layer that leaves you this nice self-suspended membrane. And this object is very interesting from the point of view of optical properties. What is also interesting is that, I will show you later, that this could enter in a CMOS foundry. And then that is important. Okay, so let's see the first difficulty. The first difficulty is that the 2D object is not, truly speaking, a real photonic crystal in the sense that it's not possible to have a full forbidden band gap. And actually, that is this dispersion diagram here shows you that and only this band gap only for one polarization. For in this case, this is a slab of holes. It was calculated that you have only for the TE polarization. And then you have another problem is that you have this gray area that represents what is outside the light cone, what is in the light cone. And we already heard about that outside the light cone, you have radiation. And radiation means that anything that is outside light cone is going to leak out. So you have this kind of red modes here that are leaky modes and are responsible for intrinsic losses. You don't want that. So design is important to try to get only to work with modes that are the blue kind, that are outside of the light cone and do not radiate. So this was brilliantly demonstrated by the people in the group of Professor Noda in Japan. They just shown that what happens if you just move 2 holes here. This is a defect, so it's a photonic crystal. You have a missing hole. This makes a defect, so you have a resonance that is localized. And then you move these holes, and what happens? You look at Q factor of the Q factor, the quality factor of the cavity, and you see that is changing a lot. So you go from poor Q factor to very high Q factor. And this is because what is happening is that you are playing with the distribution of modes in the reciprocal space and eventually end up with a configuration where you minimize radiation, out-of-plane radiation. And just to give you a sense of how far they went, they came up with a design with a Q factor of 10 million. And translated in another way, put differently, this means that you are trapping light in a wavelength diffraction limited volume over 10 nanoseconds, which means 3 meters of propagation in free space. So it's really, really an impressive way to localize light. So what we can do with that, however, if we are not able to couple light in and out to those structures, and the difficulty is that you have a large numerical aperture in the photonic crystals and a huge mode mismatch with respect to free wave propagation. And that was actually solved. So you have you can see here different implementation. This is a photonic crystal. This is a taper. And this goes straight to a fiber. And you can show here more than 50% coupling efficiency. This was our own solution. This is just a model, very compact model taper. And that was in the group of Professor Lukin in Harvard. They were able to demonstrate more than 90% coupling efficiency in photonic crystals. Okay, so the other criticism was, well, you will never able to mass produce it. And actually, this is what has been done by Professor Baba, again in Japan. They were pioneering fabrication of photonic crystal in a CMOS process. And this is a photonic crystal, can you see here? And all around you have electrodes and heaters so that you can modulate the distribution of temperature all around. What does it mean? It means that you change the refractive index, and if you change the refractive index, you change the dispersion. And why it is important? Because you can make a tunable delay line. This is a tunable delay line that is only 300 microns long, but can be tuned by 50 picoseconds. Basically, it looks like this thing could extend from 0 to 1.5 centimeters, and with a speed of microseconds. So it's really amazing. And this is because using the so-called concept of slow light that is possible owing to photonic crystals. Another aspect here is the fabrication of high Q cavities in CMOS process. And that is something that we made recently. We just sent a design to IMEC, and they put this
inside the box, what could we do in order to manipulate the constitutive parameters of electromagnetic interaction of wave and matter, like what Nader was talking about? How do we manipulate that to come up with new stuff, right? So one of the things that we did was to consider not only just material and dielectric, but also try to change by using metallic structures, metallic components in a periodic fashion, loading them with lumped elements, active elements, passive elements, nonlinear elements, now to be able to create some of these things that nature would not offer you, or if nature did, it would be specific to some frequencies and you wanted it to have at your own desired frequencies. So these embedded circuit metamaterials enabled us to look at and develop, for example, magnetodielectric materials. If you look at ferrites would have very nice properties up to about 400, 500 megahertz. Beyond that, if you wanted it to have a high mu material, you have no access to anything that nature could provide you. So how is it that we could go and develop that? And just one example, when we early on looked at, let's say, magnetodielectric material, if you design a patch, people who wanted it to make very small antenna for GPS receivers, for example, they had to use very, very high dielectric material in order to reduce the size of the patch. As a result of that, yes, you can do that, and with some trick you can also match it, but what you are reducing when you miniaturize the antenna, you lose the bandwidth. So there is a trade-off always between how small you can make an antenna and how much bandwidth you can get, and also the efficiency of antenna. Material, miniaturization is proportional to the index of refraction, which is the product of a square root of mu and epsilon. So I could accomplish miniaturization if I increase epsilon and at the same time increase permeability of the material. That I can do that, but what is more important is that if I just use high dielectric material, the impedance mismatch between the dielectric material and the surrounding is going to be significant, and the wave gets trapped inside the patch antenna, for example, or any other type of antenna that you use. If you want to release that energy, if you also increase mu at the same time, since the impedance is proportional to the square root of mu over epsilon, if mu is equal to epsilon, then you could have a very nice match, and then the bandwidth would go up. So if you do a simulation of the same material, if you want to make a lambda over 10 antenna, either you can use the electric constant of 25 or use epsilon 5, mu 5, and then the same size you are going to get, but look at the increase in the bandwidth is tenfold. Right? So it is important. So if I had, let's say, a material that would give me mu equal epsilon to 5 around 1.9 gigahertz, then I could suddenly increase the bandwidth by a factor of 10. So how do we do this? This is how you can envision wave in space. So if you have a plane wave that is propagating into free space, you can sort of compartmentalize that problem by looking at these structures. So if I have metallic structures that are perpendicular to electric field that does not impede propagation of electromagnetic wave, if I put fictitious magnetic conductors perpendicular to those, for which magnetic field is going to be perpendicular to, that does not impede the wave propagation. Therefore, the wave propagation in space can simply be examined by wave propagation in what we call a wave cell made up of a PEC and 2 PMC around it. But the neat thing about this type of approach, or the way that we look at it this way, this has a very interesting or a simple representation in transmission line, for example. So this can easily be modeled. I have a conductor, and then a wave would propagate in that, a TEM wave, and the model for that is a simple transmission line. So if I had a structure, so for example, a periodic structure where I had metallic traces and then some active or passive components loaded with these structures, if I put them periodically and filled my space like that, I could also look at a basically compartmentalization like that, come up with a wave cell like this, and then try to come up with an equivalent circuit for it. The reason we look at the equivalent circuit, because then these complex electromagnetic wave solutions can be simplified in terms of circuit analysis. And when you look at the equivalent circuit of that, you have that inductor, you have this metallic trace. A metallic trace has associated with it an inductance. There is a mutual coupling between this inductor and that inductor. If this is a capacitor, for example, this could be a varactor, so I could make my medium even tunable. I can put a capacitor there, probably there is a little bit of resistance in there, and this other capacitance, and that was capacitance between here and there. Just this simple model can change the permeability and permittivity of the material in a very interesting fashion, and you can basically design that by changing these parameters. You could get any mu you want, you can get any epsilon you want, you can make it chiral material, you can make it nonlinear material, you can make it anything that you want, but just simply loading the medium like this. So of course, since this is a simple model, now I can have the knowledge of my circuit, my electromagnetics come into the picture. How do I compute that capacitance? How do I compute that inductance? We can come up with all of these things, very easily. And then you can come up, for example, with an effective mu that is proportional to this plasmonic resonance, proportional to 1 over a square root of that inductance in that loop, times the capacitance of the loop. So if this is a varactor, I can change the plasmonic frequency. And when you look at, for example, the variation of this mu with frequency, now you have a mu material that is non-zero out of a non-magnetic material, just having a metallic structure in there that you could basically accomplish and get any mu material you want over certain bandwidths. Of course, the bandwidth is smaller. You have to play other tricks if you want to get higher mu. And also you get that imaginary part of mu, which is proportional to the quality factor of that circuit. At the same time, you can control the effective capacitance by choosing that gap between the loop and, for example, the loop adjacent to it, or that metallic, fictitious metallic structure I will put there. Now, so this region, for example, now you have a magnetodielectric region. Now, beyond the resonance, so once you hit the resonance, you would end up getting also a negative mu. So negative mu means no propagation, which means the material is going to be band gap structure, right? So you can have a band gap structure with a relatively very wide bandwidth using this type of material. So you can do all sorts of different interesting things just using this type of a structure. I'll show you that how we were able to generate a full duplex macro radio repeater using this trick. So we use, for example, this magnetodielectric. We just printed these on PCBs. This is a loop. These are the interdigital capacitors that we have. And indeed, we can reduce the size of an antenna by a factor of 6 and 7. This is the mu that we wanted to choose. That's the epsilon we wanted to choose. And now you can, for example, create a VHF type antenna that is extremely small. You can make them compact, and you have very relatively high efficiency. You know, you get 25% efficiency. And as I mentioned earlier on, once you make an antenna very small, efficiency is suffered, but you get better bandwidth than if you were just to use, for example, epsilon material. So how did we use, for example, this technology? This is very recent that we had a center on robotic microelectronics. So we wanted to make these small robots, an ensemble of them to cooperate and go, for example, in a military operation to gather information. One part of that problem when you don't have infrastructure for your communication, when you don't have cell phones, you are relying on an ad hoc communication that is basically very much limited to the environment the wave is propagating. So how do we control the propagation environment? How do I change the propagation environment to my advantage? You know, you can basically, by placing these repeaters, so if you have a transmitter, it wants to communicate to another node through a very complex environment, you know, what you want to have is to place a bunch of repeaters around, so you would establish a line of connection between, let's say, an intended transmitter to a receiver. The current approach has been just to increase the power. If you have attenuation through, let's say, building a structure, what you have to do is to increase the power. But these are very low power robotic platforms, and in order to enable such communication to work, we needed to come up with a two-way communication through these radio repeaters. That these radio repeaters are basically sub-wavelengths, very, very small, very, very low power radio repeaters that you could place between the transmitter and receiver like a breadcrumb that you leave behind. So at any corner, let's say when the robot goes, the soldier goes, they can drop one of these radio repeaters and to ensure that they change the communication to their own advantage and having a transmitter and receiver in between. The architecture of that repeater is very simple. One antenna for transmit, one antenna for receive, and a high gain amplifier between transmit and receive. And that's how you can increase, you know, the connection, right? And it's two-way because if we make both antennas to be omnidirectional, independent of where the wave is coming, you would get that amplification and transmission. So the challenge is how to increase the isolation between transmit and receive antenna. And for that, we are using this embedded circuit metamaterial that operate in band gap region. One of the things that we had to develop was to create antennas that do not have any vertical profile but can predominantly transmit vertical polarization, because that is a preferred polarization for communication. If you transmit horizontal polarization, ground reflection cancels out the direct signal. Whereas for vertical polarization, that is not the case. The difference could be as high as 50, 60 dB. So how do you make these antennas that are very, very small in height and yet produce vertical polarization? So we developed this type of antenna. We call it miniaturized multi-element monopole antennas. If you consider an open-ended, for example, stop, if this is about lambda over 4, you have open circuit field, the current goes here to 0. However, you have a maximum current that goes through, let's say, this shorting pin. And the feeding structure is right there, so you can excite that. But the current that would get excited on this pin would be on the order of 10 to 50 times larger than what you can put in a direct feed. And that's why this very, very small Hertzian dipole can radiate very efficiently electromagnetic wave. You can see that, for example, this antenna, it's a 2-arm antenna that can produce an omnidirectional radiation pattern. It has very, very high gain compared to the dimension of this antenna, which is on the order of lambda over 20 in lateral dimension, and lambda over 70 in vertical dimension can still give you very, very high gain. And as you can see, the total gain is predominantly by vertical polarization and with omnidirectional radiation pattern. So that embedded circuit metamaterial that I was talking about, that you have a loop and a capacitor, and we said that if you operate this above its plasmonic resonance, this material becomes a band gap structure. So in a substrate, what you have a transmitter, let's say you have a receiver. This is sub-wavelengths. This is lambda over 3, right? So this is very teeny tiny structure. So if you place that in there, you want to increase the isolation between this transmitter and receiver. And if you place one of these layers in between, you can inhibit the flow of magnetic energy or surface waves between them. If you don't have, for example, this embedded circuit metamaterial in there, this is the current distribution. Once you put the embedded circuit metamaterial, the current loops around and comes back, and you basically do not have isolation. So you can achieve 40, 50 dB of isolation just by putting a very teeny small layer of this structure in there. In the far field, however, there is no. So this looks like basically a magnetic wall between the two antennas only in the near field, but not the far field, so that both antennas have omnidirectional radiation pattern, but they don't see each other very near to each other. So that was basically the enabling technology to allow design of such structures that would give you more than 40 dB of isolation between 42 dB. Between transmitter and receiver, you could put 42 dB gain. We place these on robots. We use, for example, a Zigbee radio that could measure, for example, radio signal strengths. We let that to go. So, for example, if a robot is a transmitter here, we have a receiver on a robot. We ask the robot to go and measure the field strength everywhere. And that is the field intensity. We measured around minus 90 dB here. Once you put, for example, one repeater there, now the field strength is increased. Once you put two of them there, now you can have signal coverage beyond the buildings and so on and so forth. So basically demonstrating that this technology can really enhance signal connection and transmissivity. Another application that also Ahmed referred to as was these reactive impedance surfaces. These are also a new engineered type material with which you can do not only signal control, but also antenna miniaturization and connection. People have been looking into two categories when they wanted to design or suppress surface waves. They will look at PEC. Of course, we design antennas on PEC. And if you want to have a low profile antenna, you would get either very low bandwidths or low efficiency, or PMC. However, you'll see that maybe these two are not the optimum configuration for antennas. Basically, what you want to do is to look at a reactive impedance surface. And as I will show you, for example, the advantages that are given by these reactive impedance surfaces, not only for antenna miniaturization, but also maybe for even enhancing the gain of the antenna and performance. Just to give you an example, if you have a simple dipole in free space, you have this radiation, you can match that half-wave dipole very nicely. If you put a horizontal antenna on a ground plane, of course, this ground plane short circuits the antenna, no radiation, extremely difficult to match. If you put a PMC over a ground plane, you can have very good radiation, actually, theoretically. However, still matching this structure is very difficult. The reason is that there is an image of this current structure underneath that is interacting with the antenna, and there is a lot of stored magnetic energy in that medium that makes matching this antenna very difficult. However, there is an alternative, as I said. The alternative is what we call the reactive impedance surface. What is a reactive impedance surface? So, for example, for PEC, if I choose impedance to be 0, tangential electric field is 0. For PMC, if I put impedance equal to infinity, tangential magnetic field is going to be 0. But in between, there is a relationship between electric field and magnetic field. And if you want the total reflection and no power loss, what you want to do is to make that pure imaginary, so as what we have shown. So we have worked on the theory. Actually, we developed this analytical result that shows that you can find an image. If you have a PEC, for example, a point charge here, you have a point charge as an image, similarly to for magnetic field. However, if you have a impedance surface, the image gets distributed at the image point. The image at the image point actually would have a current distribution in the complex Z-plane, right? And interesting enough, because that is distributed, its interaction with its own source can be manipulated and controlled, right? That is the whole point, that actually the image of the current is not a point source, but it's a distributed source in the complex Z-plane. And that can be quite advantageous, because if you look at the interaction of an antenna and its image, if you have a PEC, you have a very strong interaction. If you have a PMC, you have a very strong interaction. But there is an impedance where you can minimize the interaction between the antenna and its image. And that is the best place, because that's where you can achieve the highest bandwidth for that antenna, get the total reflection that you want, and also, as I will show you, we can miniaturize the antenna. Why? Because if you want to operate an antenna, for example, at sub-wavelengths, let's say a dipole appears mostly capacitive, right? If I have an inductive reactive impedance surface, with the inductance of the surface itself, I can compensate for that capacitance and shrink the size of antenna at the same time. So I can get bandwidths, I can get miniaturization, and all of this can be accomplished at the same time, which seems, but how do you generate things like that? How do you get, this is the simplest form of a reactive impedance surface. You have a periodic structure of patches that is behind a short-circuited metallic structure. If, for example, you put a shorting pin here, that becomes similar to the mushroom structures that have been developed in the past by Dan Sievenpiper and Dr. Jablanovic. The operation of this is rather simple. You have these patches, adjacent patches. You have a capacitor, you have a piece of transmission line, and that is short-circuited. A piece of transmission line, when you look at it from this side, you know that is an inductor. So you have a parallel LC, and of course, if you have a parallel LC, depending on where you're operating in frequency, the surface can be inductive, or above resonance, it can be capacitive. So with this simple structure, you can design a reactive impedance surface. Reflection coefficient from this surface magnitude is always 1, but the phase can be anything that you want. And you can tune this in order to accomplish, for example, any impedance surface that you want. If you put that same dipole over reactive impedance surface, you can get perfect match, you can increase bandwidth, you can get unidirectional radiation pattern very nicely. So we use this, for example, in design of patch antennas. This is a patch antenna. You can have a substrate of dielectric of 6. We have this periodic structure of these patch elements that creates basically that reactive impedance surface, and then you can design a patch antenna that is lambda over 10, but it shows efficiency of 93%, right? And a gain of 4.5 dB. There is no patch before this that could, for example, not only give you that miniaturization by this factor, it gives you significant bandwidth, 7% bandwidth for an antenna this small. So we are accomplishing both miniaturization, high efficiency, and high bandwidth, which was not possible before. Another type of structures that come into the picture are these miniaturized element frequency selective surfaces that we developed, again, many years ago. But we call these electromagnetic skin because we wanted it to use the macroscopic effect of these. And since these are sub-wavelength structures, we demonstrate that interaction of wave and matter is very much localized, unlike many periodic structure where you have Bragg modes and then you have interaction of all these Bragg modes that would propagate along the surface. They were very much dependent on the angle of incidence. They were very much dependent on polarization of the wave and things like that. So we wanted to develop these skins or electromagnetic structures that were very low sensitive to angle of incidence. That is very important because for many applications, you don't know what the angle of incidence is going to be. You wanted it to be able to put this very closely to the electromagnetic sources, and therefore low frequency coupling could take place. You know, if you have an FSS, you need to have so many structures of these traditional frequency selective surfaces so that you would see the effect that they would produce, for example, in filtering. Here you don't have to have that. And then another very important thing is that these are harmonic-free structures, right? I mean, if you use traditional frequency selective surfaces, you have response at F0, you have a response at 2F0, and so on and so forth. These structures do not have harmonic responses because they look like lumped element circuits, right? And then thin, flexible, reconfigurable, switchable, tunable, metamorphic structures that all can be designed, and we have demonstrated them in practice. So a very simple structure of this that you can show. I showed you that if you have, a bunch of metallic patches, you can create a capacitance in space. If you have a bunch of wires in free space, you can have inductors, magnetic field perpendicular to this would circle around and effectively give you an inductance. So if you simply just, the first idea that comes to your mind, how do I make a bandpass filter? You have a patch, you have, let's say, a wire behind it. The equivalent circuit is this. You can try to design a bandpass filter. So for example, if you cascade two of these with a spacer, this is an impedance inverter. In filter design analysis, you can show a very nice bandpass characteristic. By the way, this was just simulated and calculated by a calculator using that circuit model, and you can compare that with FTTD and other full wave analysis, and smack goes on it. Here you see a little bit of, we wanted to examine the variation of this filter, for example, as an angle of incidence. You see there is a little bit of change in angle of incidence when you go from normal incidence to the structure to when you go to 75 degree. The reason, the culprit is basically this quarter wave impedance transformer. So we wanted to get rid of that so that you could completely get rid of these structures. So we looked at higher order filtering response. Instead of moving these layers slightly away, one of the things we are doing, instead of using patch, we are using loop. Because loop by itself is a series LC circuit. You have an inductance there and you have a capacitance there. That is the capacitance and that is the inductance of a loop structure. When you put another wire, you have another loop structure. And if a spacing between this wire structure and loop is small, you get both electric and magnetic coupling to it. So for example, you have a capacitance and you have a magnetic coupling. And now this a single layer structure, very thin, this is the thickness of this layer could be as small as lambda over 50, can give you a very sharp response plus a null in there. And if you make a capacitor, a varactor, if you place it in between these two, you can also make this structure to be tunable. So you can tune your frequency in anywhere you want. So you can design also other types of a structure. You can use this in order to make, for example, a reflector array. We can design and test these things. This is not localized, but depending on the size and the structure of these, you can choose the phase. So locally, you can change the phase of the reflected signal, and you can pattern these on the structure. Locally, for example, each wave, when you look at the reflection, the correction phase is done, and you can accomplish, a planar, for example, reflector using this type of a structure. I see that I'm running out of time, but you could use other type of a structure. For example, this is the last topic I talk about. You can use these structures in order to, for example, the phase of reflection from adjacent layers to be out of phase. So you can get a phase of 0, for example, from white structure, and then phase of 180 degree from the blue structure. And this in phase, out of phase cancellation would reduce the radar cross-section significantly. So you can accomplish that by a 2-layer structure. You can design these things, and you can see the radar cross-section of structures like this over the entire biostatic pattern. These are non-absorptive radar cross-section reducers that you can put on specular surfaces, for example, on your aircraft, to completely destroy the coherence and get the radar cross-section to go down. That's it.
Thank you very much. This is the standard habit of professors to have a lot to say, and my students are used to it, that I always run over the time. We will move on to the next presentation, which is by Dr. Ganapathy from Swarthmore College.
All right, thank you so much for the invitation to be here, and congratulations again to Professor Jablanovic on receiving the Franklin Medal. Today, I'm going to talk about some work that I did in Professor Jablanovic's group when I was a graduate student at UC Berkeley. And currently, right now, I'm at Swarthmore College, which is just right outside Philadelphia. And I will be talking about some joint work in achieving very high efficiency photovoltaics. And towards the end, I will bring in how photonic crystals can help us in getting even higher efficiency in photovoltaics. So to motivate why we are really concerned with very high efficiency in solar cells, I always like to start with this plot here, which shows our cumulative global solar capacity starting from 2006. And as you can see, that solar capacity is increasing exponentially. And on this graph, I have numbers up till 2015, but if you check the numbers for 2018, you can see that we've gone from 250 gigawatts of installed solar capacity to about 480 gigawatts of solar capacity. So that solar capacity is really increasing very rapidly. And what this means for us as scientists and engineers is that a very small increase in the efficiency of solar cells can have a very large impact. So it's very important to keep on increasing the efficiency of solar cells. Another interesting plot is shown here. And this is a plot of the breakdown of the different costs involved in solar electricity. And so what I have here is this total pie represents the total cost per watt of solar electricity. And I've started from 2009 and I have numbers to 2015. And what's even more interesting is the breakdown of this total cost. So here in maroon is the module cost, and that's the cost of the actual solar cell itself. Here in gray is the cost of kind of everything else. So things like the wiring, the installation, the land, the maintenance, it's all in gray here. And what you can see in 2009, so just 10 years ago, the module cost was over half the cost of the total solar electricity. So what that means is that if we can have very cheap solar cells, we can reduce this module cost and reduce the cost of solar cells. However, if you look in 2015, this module cost has dropped to about a third of the total cost. So really what's dominating here are these overhead costs. And what this says for us is if we can create higher efficiency solar cells, we can reduce costs because we can drop these overhead costs. And what this also means is that it's not really worth it to create cheap solar cells that are less efficient because the overhead costs are dominating. So a cheap solar cell that is very low efficiency is not very useful. Okay, and so going here, we can look at what has happened to solar cell efficiency, starting from when the numbers were collected in 1990. And if we look at this period from 1990 to 2007, we can see that the solar cell record efficiency, so this is the efficiency of solar cells under unconcentrated sunlight, we can see that the solar cell efficiency basically stagnated through this time period. And then suddenly in 2007, something happened and the efficiency started to climb. So what I want to talk about is some of Professor Jablanovich's work in figuring out how to get this efficiency to increase starting in 2007. And then I want to talk a little bit about some of our joint work in more recently achieving a record efficiency for solar cells with multiple materials. So this is a graph of a solar cell with a single material, and that single material is gallium arsenide. And a few years ago, we achieved a 38.8% efficiency record for solar cells with multiple materials. So I'm going to talk about a little bit how the innovations in this time period with a single material solar cell led to this innovation right here. And then I'll conclude with talking about how two-dimensional photonic crystals can perhaps make us have even more efficient solar cells. Okay, so let's get into a little bit the physics of solar energy. So this is the current voltage characteristic of an ideal solar cell. So an ideal solar cell has a band gap about 1.4 electron volts, which is approximately the band gap of gallium arsenide. And in this ideal solar cell, we can look at two important points. So we have one point right here, which is called the short circuit current condition. And if we operate our solar cell here, so if we load our solar cell so that it's operating right here, we maximize current, but our voltage is zero, so our power output is zero. And then another important condition is right here. So that's called the open circuit voltage condition. And if you operate there, you maximize the voltage, but the current is zero, so again, power output is zero. So what we do is we load our solar cell, and we sacrifice a little bit of open circuit voltage and a little bit of short circuit current so we can operate right here at the maximum power point. And what we need to do to get a very high power output and also a very high efficiency is to both maximize our short circuit current and our open circuit voltage. Okay, so let's take a look at this very, very simplified picture of a solar cell. And what it is we have some sort of substrate. So with gallium arsenide solar cells, you take kind of a poor quality gallium arsenide substrate, and you epitaxially grow a thin film, so that's going to be your solar cell on top of it. And the solar cell is probably about 2 microns in the case of gallium arsenide. Okay, so at that short circuit current condition, you have light coming in from the sun, and it enters the solar cell and is absorbed. And the picture at short circuit current is relatively straightforward. What happens is those photons from the sun are absorbed, creating electron-hole pairs, which are then collected as current at the contacts. And I want to note that I've drawn these rays coming in, and they're refracting towards the normal. They're getting a little bit more straight inside the material because your optical index of refraction inside the solar cell is much higher than the air outside. All right, so the picture of the solar cell at open circuit voltage is a little bit more subtle. Okay, so in this case, we have the same light coming in, and it's absorbed in our solar cell, creating electron-hole pairs. But at open circuit voltage, you're not collecting any current. So those electron-hole pairs are forced to recombine. If you have a really good quality material, such as very high quality gallium arsenide, those electron-hole pairs can recombine radiatively and produce a photon. So they produce these internal photons with energy around the band gap of your material. And these internal photons can actually be reabsorbed and re-emitted again inside your material. Okay, so you have your solar cell, which is grown on some substrate. So what happens is that eventually these internal photons, say you have a very perfect material, eventually those internal photons either escape out the back into the substrate and are parasitically absorbed, or in very rare cases, those internal photons can escape out the front. And I say that's very rare because of this index mismatch between your solar cell and the air outside, most of the internal photons, upon hitting this interface, will experience total internal reflection. So most of your internal photons will be escaping out the back substrate, which is index matched to your solar cell. Okay, so what we have here is we have these internal photons which are escaping out the back. And even though this is an ideal material solar cell, these photons escaping out the back actually represent a loss process for the solar cell. Okay, so we have a perfect material here. We have really no excuses for getting high efficiency, but we do have a loss process with these photons escaping out the back substrate. And kind of the intuitive way to think about that is everything in thermodynamics is about reciprocity. So we are absorbing photons from the sun through the front surface. By thermodynamics, we are forced to emit back out the front surface. It's a reciprocal process. However, any emission out the back is a loss process because we're not absorbing photons through the back. We are, anything that's emitted through the back is not thermodynamically required, so it's a loss. So what we need to do, as pioneered by Professor Jablonowicz, is to remove that back surface and replace it with a highly reflective back mirror. And just intuitively, you can see that the voltage has increased in this picture because voltage is logarithmically proportional to concentration of photons. So you can see in this picture that the concentration of photons has increased from this picture right here. And we can be a little bit more precise about this by looking at this term right here, which we call eta external, which is the ratio at open circuit voltage of the number of external photons absorbed, the number of photons emitted to the number of external photons absorbed. So if you get for every absorbed photon at open circuit voltage, you get a photon back out, you get an eta external of 1, which means that your ideal open circuit voltage, a theoretical prediction outlined by Shockley and Queeser, will not be penalized. But if you have any eta external less than 1, you penalize your open circuit voltage by this factor, thermodynamic factor of kT over Q. And so how experimentally do we get that solar cell off of the substrate? This was work by Professor Jablonowicz in 1987, and they pioneered this idea, which Dan alluded to, of epitaxial liftoff, where you take your gallium arsenide substrate, and before you grow your gallium arsenide heterostructure, you grow this very thin sacrificial layer of aluminum arsenide, so just about 100 nanometers. And you can submerge this whole structure in dilute hydrofluoric acid, which selectively etches away that aluminum arsenide and allows your solar cell to pop off so you can then apply a highly reflective back mirror. Professor Jablonowicz founded a company called Alta Devices that created these flexible gallium arsenide solar cells. So these are very thin. These are about 2 microns. And these solar cells have reached a record efficiency of 28.8%. Oh, sorry, 29.1. Okay, I should have gotten the most recent numbers. All right, so they're very highly efficient, and they're very, very close to the theoretical efficiency that you can predict from solar cells. Okay, so we can go back to this plot right here of solar cell record efficiency and kind of see the story of what happened. So from 1990 to about 2007, we did have very high material quality. There was very good gallium arsenide in this time period. However, there was not much thought given to the optical design of the solar cell. There was not enough thought given to the open circuit voltage. So what happened in this time period right here is when we first started seeing epitaxially lifted off solar cells appear on the scene. And then the voltage really started to increase. And all of these voltage records in this last time period are held by Alta Devices. And an instructive plot is to look at the corresponding open circuit voltage. So over that time period, we saw that the open circuit voltage increased. But if you look at that same time period at the short circuit current, you see it's actually stagnated in this period. And the short circuit current right over here is actually a little bit lower than the short circuit current over here. So it was really the open circuit voltage and that consideration of the optics of the solar cell that allowed us to reach really high efficiencies. Okay, so now I want to talk about how during my time in Professor Jablonowicz's group, we applied that understanding from building these efficiency records to get a 38.8% efficiency record. So I'm going to go from single material solar cells now to multiple material solar cells. So these are called multi-junction or multi-band gap solar cells, where you stack different absorbing materials. And you stack them so that you have your largest energy band gap on top. So you absorb the very high energy photons first, and you let the lower energy photons, they just pass through those higher band gaps, and they're absorbed by the lower subcells of this device. And the reason that this gives you higher efficiency is because your photon energies are better matched to the band gaps, so you lose less to thermodynamic losses. Okay, so what we want to do is we want to apply the understanding that we got from the single junction solar cell to this multi-band gap solar cell. So one obvious thing here is, okay, well, you could remove that growth substrate and you could replace it by a highly reflective back mirror. And what this will give you is this will give you a voltage increase in this bottom subcell. However, that's not enough for us. We want a voltage increase in all of these subcells. So obviously you can't just take a reflective surface and stick it between these subcells because that would hinder the lower energy photons going through. So what we need is a frequency selective intermediate mirror that will reflect the internal photons of each subcell without hindering the flow of those lower energy photons to the bottom subcells. And so this is not a very easy task to create a broadband frequency selective intermediate mirror. But what we can do is we can turn to some inspiration from Snell's law. And what Snell's law tells us is that, let's say we have some sort of high index semiconductor surrounded by air. If we have some external light coming in, it's going to refract towards the normal. It's going to refract into the escape cone of the material, and then it's going to go out with the same angle it came in. However, if we have an internal photon, that internal photon can see the full phase space of the material. It can be emitted at any angle. There's no angular selectivity when you recombine in the material and then you emit. So that internal photon can be at any angle within the material. So what that says is when the internal photon hits this air interface, it's most likely to experience total internal reflection. There will be very few internal photons within this escape cone that will make it out of the material. And so Snell's law gives us this angularly selective mirror, which basically gives us frequency selectivity for free. So with an air gap, we can create a very nice intermediate mirror. Okay, so together with Eli and an undergrad, Chi-Sing Ho, we proposed this idea of an air gap intermediate mirror. So this is a dual band gap solar cell, so there's two absorbing materials. And so in our naive design, we just grow our two cells on substrate. We apply an anti-reflection coating, and we get a theoretical efficiency of 41.1%. So that's the maximum theoretical efficiency you can get if you grow on substrate. So if we remove that substrate and apply a highly reflective back mirror, we can jump up about 3 percentage points absolute in efficiency. And if we go even further and we apply this air gap intermediate mirror, so it's an air gap sandwiched by anti-reflection coatings, we can pick up another about 2 percentage points in efficiency. So just taking a closer look at the science there, if we look at the last two cases with and without the air gap, and we look at the top subcell in these two cases, we can see that the open circuit voltage from no air gap to an air gap gave us about 70 millivolts in voltage, which is quite a big deal for a solar cell. And that voltage increase causes an efficiency increase. And you may notice that for the air gap, we get a slight decrease in short circuit current of that bottom subcell. And that's because those internal photons can be absorbed through the bottom subcell and converted to current. However, that is not the dominant effect. The dominant effect is the increase in voltage, which gives us an increase in efficiency. And the most exciting part about this work was that our collaborators at the National Renewable Energy Laboratory near Boulder, Colorado, decided to experimentally verify this result. And they had a 4-material solar cell, and they put an intermediate material between two subcells. So at low index epoxy, which is just easier to mechanically implement than air, sandwiched by anti-reflection coatings, and they achieved an efficiency record of 38.8%, which is the highest efficiency for a solar cell under non-concentrated sunlight. Okay, so far I've been talking about very ideal materials that can absorb photons and then radiatively recombine. So generally, materials are not so ideal. You will lose those internal photons to non-radiative recombination at some point. So even with a non-ideal material, we can use optical techniques to figure out how to boost the efficiency. And one thing that Professor Jablanovic has also pioneered is this idea of texturing the surface of solar cells. So when you texture the surface of the solar cell, you can actually increase the absorption of these external photons. And because you can increase the absorption, you can make the solar cell thinner without hurting your short circuit current. And some kinds of non-radiative recombination, such as Auger recombination, scale with the volume of your cell. So you can decrease non-radiative recombination, such as Auger recombination, without harming the absorption of the external photons in your cell. And in a non-ideal material, that voltage increase can be around 100 millivolts of voltage. So going into light trapping a little bit more. So this is a figure from Eli's seminal paper from 1982. And why does light trapping cause you to increase your absorption? And so if you just look at a flat solar cell, or just a flat surface, the light comes in and it sees a single pass through the material. So it can only be absorbed in that single pass. However, if you just randomly texture the surface, the light comes in and can bounce around many times due to total internal reflection. And we get a factor 4n squared, so this is called the Jablonowitz limit, and n is the refractive index of your material. So in a material such as silicon or gallium arsenide, the refractive index is 3.5, so you get 50 times increase in your path length. You basically get 50 times absorption enhancement. And so this idea is pretty powerful. You can make your solar cell 50 times thinner, you can increase the voltage, you can reduce material costs, and is pretty much used in all silicon commercial solar cells today. However, there's a slight catch, and the catch is that this limit only works in the ray optics limit. So it only works when your solar cell is much thicker than the wavelength of your light. So this is great for silicon solar cells, which are indirect band gap and have to be thicker anyways to absorb your light. However, for something like gallium arsenide, you have a solar cell which is about 2 microns thick. If you want to decrease that by 50 times, you're on the order of 100 nanometers. So your solar cell thickness is on the order of the wavelength of your light. You now have to worry about wave effects. Okay, you need to consider full wave optics. And in this regime, what we were trying to figure out was we don't even know if the 4n squared limit could hold. And even once we found what the limit of absorption enhancement was, we didn't know what the ideal texture would be. So in the ray optics limit, just a random texture is the best you can do. You can't do better than a random texture. In the subwavelength, it's possible that you could do better or worse than 4n squared, but it's possible that a random texture is not optimal. You would need to engineer the texture. So continuing on the theme of previous talks, we look to inverse design. So inverse design says we have some sort of figure of merit and we want to find the structure that optimizes that figure of merit. So we want to find what surface texture can optimize our absorption. So we computationally optimize the surface texture function of a solar cell. So this is just the structure that we used, which was an anti-reflection coating, a solar cell with a back surface texture, and just a dielectric filler. Okay, and the question we asked when we do this optimization is where should we add or subtract material along this texture, keeping the average thickness fixed. So we fixed it at 100 nanometers in order to enhance the absorption. And one of the innovations in Professor Jablonowicz's group was using the adjoint method in inverse design. And just to summarize, the adjoint method lets us get the gradients of all our shape parameters in one go. So instead of having to emulate our structure for figuring out for each of these points, we just have to computationally simulate our structure once to do this optimization. Okay, so just to show a little video of one example optimization. So we optimize the absorption over a frequency band, and this shows the evolution of our surface texture. And one thing we did was we optimized for very good broadband absorption. So a solar cell can't just be a resonant device, it has to absorb well at all frequencies. So in our optimization, we always optimize for the worst performing frequency, getting a very nice broadband response on this solar cell. Okay, so just to summarize the result, so the ray optics limit is given here. And with angle and frequency averaging, we get very close to the ray optics limit. And this work showed that even in the wave optics regime, we can get very close to the Jablonowicz limit in high index materials. Okay, so just to summarize, we first looked at how we can change the optical structure of a solar cell with back mirrors and get a voltage boost. And then we applied that to multi-band gap solar cells with these low index intermediate mirrors. And then finally, we looked at two-dimensional photonic crystal textures for light trapping. And obviously, I would like to acknowledge Professor Jablanovic as very fundamental to this work, as well as several other collaborators, both in his group and at the National Renewable Energy Laboratory. So thank you very much.
Thanks. I think the pride of any professor is to have a great student, and it is definitely a demonstration of that. Now we are reaching the highlight of our today activity, which is the talk by Professor Ilya Jablanovic. You have learned all the major contributions and the impact that he had so far. So without any further ado, I wanted to give the floor to Professor Ilya Jablanovic, who is going to talk about a new topic of electromagnetic spectra of ordinary objects.
Okay, thank you very much. Okay, I have my own green one. Okay. Well, I'm very honored that so many of you have come to hear this symposium. And it's been terrific for me to experience this. And what I'd like to do is to go quickly because we're a little bit behind time. And so let me show some of the things you know to go 1D. And 1D was actually done by Lord Rayleigh. These are things that probably most everyone here knows. And then we went on to 2D and to 3D. And got this more complicated structure, which had a three-dimensional band gap. And my original motivation was to suppress spontaneous emission, and I impressed our vice president at Bell Communications because it looked like it might have an application in telecommunications. Now, one of the things that Lord Rayleigh did is that he realized that he could get a one-dimensional band gap even with incredibly tiny index contrast. But to get a 2- and 3-dimensional, you need more index contrast. And this led to this particular editorial written by the editor of Nature. This was quite a challenge. And he said, photonic band gaps bite the dust. But even at that moment, we were already figuring out how to overcome the problems that were noticed at that time. And eventually, we overcame them. And let's see if I can get this thing started. Do we have a mouse here, or do I just use the pad? Oh, it's running by itself. It's just a little video I wanted to show that one of my students made some time ago. It's kind of eye-catching, and it shows all the different holes and the way you do it. And frankly, what inspired this was looking through models of silicon crystals. And you can see all these holes and channels in silicon crystals. And this was the discovery that the best material for electronic semiconductors is also the best structure for photonic semiconductors. So that was a big surprise to us. Now, there were some problems, though, with it, is that a band gap meant that there was no electromagnetic field, no zero-point fluctuations, and no spontaneous emission. And I came to realize that nobody wants to pay me for producing no light at all. Okay, and so we looked at other applications, and I'm going to just mention two applications. One of them is actually used, this is something that you may have used inadvertently yourself, is a polarization splitting coupler that is used in silicon photonics in data centers. And and the second application is not something that we invented, it came from nature. So nature figured out photonic crystals long before us, we just didn't recognize it. This is the stuff that's used in data centers, and it is basically optical active cable. So these are electrical connectors, and there's a little bulge in there, and that little bulge, you have your silicon photonics, which converts the electrical signal into photonics, and then this yellow cable is actually just fiber. And it's commonly used in data centers, and millions of these have been sold for use in data centers. So I'm going to mention one component. When you do optical communication, it's very convenient that you can string a wire, you can go around corners, but every time you go around a corner, the polarization of light inside gets scrambled. And so if you're going to do optical communication, you have to split the two polarizations and amplify them separately. And the big question is, how do you make a polarization splitter for silicon photonics? Now, the silicon photonics, you want to make everything in a silicon foundry. And in fact, this is the way it's done, is you have a grating coupler, and lines are just vertical usually. And the grating couplers go into a silicon waveguide on silicon dioxide. Now, when you do a polarization splitter, you have to be a little bit smarter. And this was actually an invention. I did not invent this, but it's a very clever thing. And what it says is you have a two-dimensional photonic crystal, and then you see the lines, the periodicity. So one polarization is sent this way, and the other polarization is sent that way. And that becomes a very important component. And this is what it looks like close up. You see the dielectric periodicity in 2 dimensions, but it also has some rather sophisticated detailed shape to it that has been optimized over a long period of time. So this component is very critical to silicon photonics. And I'm very glad that we have someone here from Cisco. Raise your hand, okay. And Cisco acquired Luxtera 2 months ago. And of course, why? Because Luxtera had managed to sell millions of chips to data centers. And so every time you check email or download a web page or have cloud services, you are going to a data center. You have no idea what's happening at the data center. But in the data center, in many cases, they're using the Luxtera chips with the two-dimensional polarization splitting beam coupler. And so I can say this is probably the biggest photonic crystal application to date, because we say we have millions of users because everybody in the world is on the internet, and they're all, and some of the time they're collecting their data by going to data centers. Now, photonic crystals were common in nature. This is opal. This is a kind of a jewel. And so they're very common in this way, but they're also common in the world of nature. And this came as a big surprise after photonic crystals got going by us engineers. The biologists suddenly started reinterpreting what they had been looking at in the colors of plants and animals, which is quite amazing. So let me show you some examples from nature. Okay, and these are some two-dimensional photonic crystals. This is from the sea mouse. This is from a bird. I'll show you more bird stuff in a minute. This is from peacocks. Very interesting. Let's just look at these animal pictures. So here we go, the peacock. Well, I'm old enough to remember when this was the symbol of color television from NBC, and was a peacock, and was discovered by a scientist in China. They looked into the feathers, and there was a two-dimensional photonic crystal in the feathers, and so that's kind of remarkable. And he showed this. And I was rather stunned by this, because I thought this was something artificial, but it actually nature had done part of it already. Now this was a relatively simple two-dimensional photonic crystal. For sure, nature could never figure out how to do the diamond structure. After all, it took 4 years. To figure out how to do diamond structure, including that photonic band gaps bite the dust. But sure enough, you have these beetles, and this one is exactly a diamond structure. Diamond-like. Face center cubic is also quite common, but there is diamond-like. And so you have this rather interesting looking beetle with this kind of iridescent skin, and that was something figured out by nature. These are actually, they also discovered a butterfly with diamond structure. And I recognize this because all my diamond structure crystals, they kind of look like this when I cut them. And so I had no trouble recognizing that. This is more about the beetle and showing that, yes, it has a band structure, although not a complete band gap. Here's one, short range order. So you look inside the feathers of parrots, and you see this structure. And this is not exactly crystalline silicon, but it is the structure of amorphous silicon. And the nice thing about it is you get your color, and it looks the same from all angles, whereas the beetle I showed you was somewhat iridescent, so the color depended upon the angle. This is much more natural-looking color. And this is like totally amazing, all these colorful birds. So this has been studied in detail by ornithologists, people who go to New Guinea to look at birds. And they have found that the blue and the white colors. So if you look at birds and you see red and yellow, most likely that's just pigment, but or some kind of absorber. But if you see blue or white, it's most likely a photonic crystal coloration in the birds. So it's kind of amazing. And it's non-iridescent. This one was figured out by the group at Fudan University in Shanghai. So I have some movies here of chameleons. So this is another example of some, let's see.
You didn't need to press it.
Oh, I didn't need to press it. It was going to run by itself.
You went to the next one, yeah.
Yeah, I went to the next one. Okay, let's see if this one works. Okay, let's go do it again. It'll start by itself. Yeah, so what's going to happen here is this is a chameleon, a lizard that is very famous for changing color, and it's basically compressing the photonic crystals that are in the skin. So this is the original color, and after a few minutes of stimulation, you see it's changed from green to yellow. Essentially compressing the photonic crystal structures that are in the skin of the lizard. I think I'm going to skip this part. I want to show this particular one is a rather amazing one. This is a bird in New Guinea. It is a male trying to mate with a female, and so he has to try to impress the female as much as possible. And you see he's got this fantastic white color, which comes from a photonic crystal structure in his feathers. And he's trying to persuade, he uses this strong coloration to persuade the female. The female is unimpressed, and unfortunately this mating failed. Okay. So this gives you a little bit of an idea of some of the things that are going on in photonic crystals. Some of it has some fun in it. And I'd like to get a little bit away from photonic crystals. And where I'm going to tell you about now is about cell phone antennas. And my original motivation was to make cell phone antennas with photonic crystals. That turned out to be not very advantageous. But so how do you make a cell phone antenna? The question arises. And so what I'll try to indicate is that ordinary objects that we experience in our daily lives, that a chair, a metal stand like that, maybe even some of the utensils back there for pouring the coffee, and all of them tend to have their own spectra. Even us human beings, we have our own electromagnetic spectra. And so you might wonder about that. So let's just go through that. And that is, of course, we're all familiar with RLC circuits, and they have a sharp resonance. And but what I'm going to say is the AC circuits are everywhere, even places you don't normally think of. So let me try to indicate an example of an object. So suppose I have a one-turn resonator. I could say, oh, that's an inductor. It's a one-turn inductor, and it's got a little bit of capacitance here, and it sort of forms a capacitor. So it's an LC circuit. If I had a loop of wire, and it had an L and a C, you wouldn't doubt that it had an electromagnetic resonance. But we can make some changes. For example, suppose we increase the spacing of the capacitor plates. Then you simply reduce the capacitance, but it's still a perfectly good LC resonator. And then you go further and you straighten it out completely. And you still have sort of a capacitor plate on top and a capacitor plate on the bottom. You still have some of the inductance on the wire. And so what this suggests is that even a straight wire has an LC resonance frequency. I'm just looking at my pointer here. It's definitely metallic, and it has its own LC resonance frequency. It's sort of a common everyday object. So the straight wire is an LC resonator. A bent nail, that sort of looks like that loop we had on the previous slide. So a bent nail is an AC resonator, but it doesn't have to be bent, could be straight like the wire. And a straight nail is also an LC resonator. So what it says, every piece of metal you ever saw is actually an LC resonator. It's more obvious if you have a paper clip because it's in more sort of a spiral, but that it has an inductance. But it doesn't have to be a paper clip. It could be any metal shape is an LC resonator. And it has a spectrum. Now, other examples. Suppose you go and you buy an inductor. You say you want inductance. Well, you'll get a certain number of nanohenries, but that's not the only specification. If you specify an inductor, you also have to specify the LC resonance frequency because the inductor, it could build up positive and negative charge. You get some capacitance, and every inductor has a self-resonance frequency, and you better look up that specification too. As well, because you need that before you buy the inductor. Now, let's go to a human being. Human beings conduct electricity because our blood is filled with ions and salt and so forth. And we have a certain height, so just from our height, we have an inductance. And you can imagine we could build up negative charge around our heads and positive charge at our feet, and that's a capacitor. So we are all LC resonators. And a car, you could do the same thing. You could have negative charges at the front and positive charges at the rear, and so a car becomes an LC resonator. So all objects are LC resonators. And now you asked about a human being. So I ask the students in my class, I tell them this, and I say, okay, what is your personal resonant frequency? Well, it depends upon their height. Right? And so if a person is about 1.9 meters tall, a half a wavelength fits in, and your personal resonant frequency is 79 megahertz. And I could have used the same reasoning for dielectric objects. And so now I'm going to make an extravagant statement that every metallic or dielectric object you ever saw is an LC resonator. Now it gets kind of personal with the students, because then I ask them, well, now that you've accepted that you're an LC resonator, I'd like to know, what is your personal Q? And now I'm being fresh. I'm being very fresh when I ask that. But it's a meaningful question to answer. So every object also has a Q, namely a radiation Q. Because if it's an LC resonator, you have AC currents. If you have AC currents, you have radiation. And it's appropriate to ask, what is the radiation Q? And so this sort of example of how a wire could act as a resonator. We said we could build up positive charge on one end and fit a half wavelength in there. And from the length of the wire, we get inductance, we get capacitance, and we get resonant frequencies. This is usually the lowest resonance of a wire. Of course, we can put two of these in a wire, and we get twice the frequency. And not only does every object have resonances, but it has a whole series of resonances that go on and on and on, all the way to optical frequencies. And every object has a spectral fingerprint depending upon the geometrical shape of the object. And the resonances go on and on. Now, in a senior level lab, they have this equipment, they have a network analyzer, and they have an object. And I'm not going to call the object an antenna because we've already agreed that every object can be an antenna. But then they go and they measure the reflection from the metal object, and they see the whole series of resonances going up to higher and higher frequencies. And usually we tend to use the first one as might possibly be useful for antennas, but there's a whole series of them. And you have here a spectral fingerprint depending upon shape. There's a better way to do it, that is with a little coil. So you just hunt around. It's a little bit like radar. You have a little coil, and you sniff around the object, and you can get the whole series of resonances just by sniffing around with a radio coil. Now, so I've tried to convince you that every object supports AC currents. AC currents require acceleration and deceleration, which therefore radiates electromagnetic radiation. And therefore, every object is an antenna and can radiate electromagnetic waves, and therefore can also capture electromagnetic waves. So it leads to the question, wow, that's the easiest antenna I ever saw. So why is it so hard to make antennas? So this is just a statement that the lowest order mode, I said it already once, the lowest order mode is the best antenna usually, and that applies to people. So now I'd like to convert the discussion, okay, if that was so straightforward, what about cell phone antennas? And so I'm going to show you things that those of us who are old enough to remember. By the way, you go to kids, they've never seen these kinds of phones. Okay, and how the cell phone antenna evolved. And I should mention that by the time you had, well, this was like the early ones, which were kind of rigid things that were sticking out the top. Okay, and this was an extremely popular one, and it was if you were really important, you got one of these, and you pulled the antenna out. Now, the reason I'm going to show you this rogues gallery of antennas is that they made hundreds of millions of these, and they had the best consultants, and they had unlimited budget, and 2 years later they decided that was really stupid, and they changed the design of the antenna completely. So let me show you the next design of antenna. And by 1998, so this is 3 years later, so what's this thing about pulling out? You just have a little stub here, okay? And you had the stub antenna. This was extremely popular for a time. And they made hundreds of millions of these as well. And they had the best consultants. And it was 2 years later, the stub was gone. We didn't need the stub after all. And so Nokia Pioneer in 2000, the antenna was missing. It was internal to the cell phone. And so it kept changing, and all I can say is obviously there's something wrong in their understanding, because they keep changing it. And if they had done it right the first time, they wouldn't have to keep changing it. So it was in 2000 I started my cell phone antenna company. I thought I was going to use photonic crystals, but they were going to end up not miniature enough for the cell phones. We worked for several years. We had very generous venture capitalists because we were making no progress at all until about 2005. The company's name was Ethertronics. 2005, we came up with an improved internal antenna that really worked well, because the one from Nokia, whoops, going the other way, the one from Nokia didn't perform that well. So we got about a 2 decibel improvement. We had a trick that had a 2 decibel improvement compared to other cell phone antennas. Now I will flash forward to the history of cell phones and cell phone antennas. We had, in 2010, we had AntennaGate, and the AntennaGate was basically Apple and Steve Jobs. He was a tyrant inside his company. He was a genius, but he was also very demanding. And he told them that, no, the skin of the phone is going to be the antenna, which is actually a very smart idea. But don't do this for the first time on a flagship product. Do it on a smaller product just to get the bugs out of it. So they had enormous bugs in it, and the phone had to be replaced. And basically, this little insulating part, this band around the outside was the antenna. This little insulating part was very much a part of it, but if you shorted your fingers across that insulating part, it was pretty disastrous. So what I have is I have a video of Steve Jobs holding a press conference. This is his press conference, and he was forced to, because all the customers were in an uproar. And basically what he said, well, it's true, our antenna is really bad, but go look at the Ericsson antenna. That one's no good either. and he made a lot of excuses. And the sad thing is he spent a day organizing this press conference. He didn't know he had only 13 months left to live. And so he wasted a day like that just making excuses for the bad antenna. Partially solved with the 4S, but you see some of the same issues coming up. And so Apple didn't have it really figured out until, let's see, this is the one where Apple figures it out. This is the iPhone 6. Many of you have the iPhone 6 right now, and it is what he wanted. The skin of the phone is the antenna. Actually, the antenna elements are at the top and bottom, so you have spatial diversity in it. And I knew he had finally, the Apple, okay, I have to tell you a little bit more about this. My company tried to sell to Apple. Now, we were by then already the biggest supplier to Samsung. And we said, oh, you have problems with the antenna gate. Why don't you let us solve the problem for you? And the reply was, we have to do it internally because it affects the appearance of the phone. We can't delegate that out. We absolutely have to do that internally. So thank you very much for your efforts, but we don't need any help from you. And so they didn't want to listen to us. And then I was wondering, when are they going to finally figure this out? And so when I saw this phone, I said, yeah, they finally figured it out. Because you'll see the key point is to have a kind of a gap. And this is like there's only 1 volt here. Why do you need 2 millimeters of insulation if it's just a volt? Let's see. Okay. So that big gap was the tip-off. So let me kind of show you what the issue is that helped make Ethertronics about 2 decibels better than the competitors. So we said that every LC resonator is an antenna. So this is, for example, from the Nokia phone. They have a circuit board in the Nokia phone, and they have an element that is sort of just below the circuit board. And I've pulled that out here as a separate function so you can see that it indeed represents a type of an LC circuit. And you build up negative charge on the antenna and then positive charge on the circuit board, and then vice versa. And this tells you one of the great truths is you might have an antenna element, but it's the whole phone itself that acts as the antenna, which is important because size, you need to get as much size as possible. Now these positive and negative charges reverse at every half cycle of the radio oscillation. So it goes back and forth, the current goes back and forth. And so one of the things that we just heard about this in the previous talk from the University of Michigan, is that the Q is very important. That is to say, you tend to get narrow band. You don't want narrow band. You want broadband antennas in a cell phone. If it's very narrow band, it could be the call will come in on the wrong frequency and you'll miss the call. So you need to at least have a Q of around 10. And so antennas are like the opposite of everything in physics. In physics, you're always trying to get the highest Q. In antennas, we're always trying to get the lowest Q. Okay, so one of the things we teach students about Q, it's the energy stored divided by the power radiated. So, well, the power radiated, you have sort of pretty good dipole here, AC dipole, it radiates. What about the energy stored? Well, the energy stored, it comes in various forms. So obviously, there's capacitance between this positive charge and negative charge, and that's a lot of charge separation. That's good for an antenna. But there's also some capacitance in here that there's not much charge separation, but it nonetheless stores energy. So you're storing useful energy, that's antenna energy, that's good, but then you're storing useless energy over this little gap. And so what you're trying to do is actually get rid of the useless capacitance. There's bad capacitance in antennas, there's good capacitance, and this is how they were making the antennas at that time, is that they had this useless capacitance which was harming the Q, okay, which was storing energy to no avail. And so a simple geometrical change, which by the way took us 4 years to realize in the company, so we were looking and looking and looking, and finally we came across this. And just simply moving this antenna element, moving it out here. And so your bad capacitance is limited by just what's in this little gap in here. The rest of it is good capacitance, a lot of charge separation, a lot of good radiation. What this did for us, it was about 2 decibels improvement compared to our competitors. And that was enough, so we put most of our competitors out of business. And by the way, we had the example of the iPhone 4 with antenna gate. Samsung would not buy anything from us without doing at least $100,000 worth of testing. So that could never have happened with that major customer. So we started supplying this to them around 2005, and the company grew and gained market share and so forth. And I'll just show you an example of the product. So this is the corner of a smartphone, typical smartphone. It's on the interior, you can't see it. And what Ethertronics did was basically to pattern metal on the surface of the plastic, and it's always a different pattern depending upon the exact geometry of the phone. And it's all these strange parasitic elements. All of them were needed in order to make it work. And if any of these elements moves by a millimeter, the phone stops working. So you have to get the exact geometrical pattern. This, of course, is that type of LC circuit is well known. Heinrich Hertz was doing this. He had his loops and his discoveries. So what ended up happening, well, this is I see it's an old slide. The company shipped 2 billion antennas with a B. So this is totally amazing. And I'm sort of in awe of the team. And now the only way to do that is through Samsung. And then they acquired, not them, it was acquired by a company called AVX, which used to be a capacitor company, and which is owned by Kyocera. So they acquired this company. And so it's outside of my hands now. But I'm very proud of the accomplishments there. So let me conclude, and that is that photonic crystals are a part of nature, and they're also part of our everyday lives in the sense that people use them whenever they access data centers. But it also has to do with something that maybe we don't teach as much as we should, which is that every object is an LC resonator. Every object can radiate, can be an antenna, and if you do it right, you can end up appearing in billions of customers' hands, which is totally amazing, and a kind of ambition that I think every engineer has, is to have something that everybody uses. So I'm very proud of that. Thank you.
Thank you very much, Professor Jablonowicz, for a very stimulating presentation today. But your legacy and your contribution is for many, many years of hard work and great ideas that you have seen how it has crystallized and has moved forward in so many different directions. I'd like to thank all our speakers, and also I wanted to shoot out to the invited guests for the luncheon. It's going to be starting at 1:10. I alerted them that we are a little bit behind the schedule, so we would be able to make it hopefully within the next 20 minutes to the luncheon. The other important aspect that I wanted to mention is I wanted to thank our sponsors, because without them it could not have happened. Naturally, with Drexel University and Villanova University, they were in the forefront, but also Rowan University, and in addition to that, IEEE Philadelphia section. And I wanted to thank the contribution of these organizers that they have helped us to provide this service to our students and our community. Once again, thank you for all your participation, and a special thanks to our speakers.